In the vast darkness of the cosmos, among stars that drift silently in ordered paths across the galaxy, there are rare exceptions, celestial rebels that defy the gravitational harmony of their environments. One of the most dramatic of these is Zeta Ophiuchi. Imagine a star hurtling through space at blistering speed, not because it was born to move fast, but because it was violently kicked out. Zeta Ophiuchi is not your average star. It is a cosmic fugitive, flung through the galaxy like a bullet from the barrel of a stellar gun. But before we continue, subscribe to the channel and like the video. There are many violent events in the universe: colliding galaxies, exploding supernovae, and hungry black holes tearing stars apart. But Zeta's story is unique. It begins not in chaos, but in companionship. Once a member of a tightly bound binary system, Zeta Ophiuchi's life was upended in an instant when its companion exploded in a supernova. That one event would reshape its destiny forever. With its partner obliterated, the shock of the explosion ejected Zeta from its system, sending it careening through the Milky Way at incredible velocity. We usually think of stars as stationary on human timescales, glimmering constants in the night sky. But Zeta Ophiuchi challenges that perception. It doesn't sit still, it tears through the interstellar medium like a rogue wave, creating shock fronts, heating gases, and disturbing the quiet fabric of space itself. And even more stunning? It's still relatively close to us, only about 366 light-years away. In galactic terms, that's practically our cosmic neighborhood. What makes Zeta's tale all the more compelling is that it isn't just about motion. It's about survival. Most stars that find themselves in the neighborhood of a supernova don't live to tell the tale. The energy unleashed in such an explosion is enough to destroy entire star systems. But Zeta Ophiuchi not only survived, it was launched, propelled out of its home system with a force that would forever set it apart. In the depths of the Ophiuchus constellation, where snakes coil around the ancient figure of the serpent bearer, Zeta now glows as a defiant reminder of stellar violence and resilience. This isn't just the story of a star, it's a cosmic biography of loss, motion, and enduring brilliance. And over the next 4 hours, we're going to trace its past, study its present, and speculate on its dramatic future. Why do stars run away? How do their motions sculpt the space around them? What secrets do they carry about death, rebirth, and the invisible companions left behind? Zeta Ophiuchi is more than just a bright point of light in the night sky. It's a celestial survivor, a high-speed traveler, and a living echo of a stellar apocalypse. Stars usually live their entire lives in the cradles where they are born, stellar nurseries rich with gas and dust, surrounded by sibling stars that share a common origin. Over millions or billions of years, they drift slowly, orbiting the galaxy with a kind of quiet majesty. But Zeta Ophiuchi defies that norm. It has no home. It doesn't belong to any cluster, any nursery, or any system anymore. It is a cosmic outcast, traveling alone through the galaxy like a displaced wanderer. And that's not by choice. It's the result of a dramatic and violent upheaval that tore it away from everything it once knew. When astronomers observed Zeta Ophiuchi and began measuring its motion, something didn't add up. It wasn't simply orbiting the galaxy like other stars in its region. It was racing, moving at tens of kilometers per second through space. And when its path was traced backward using models of galactic motion, it pointed to an origin far removed from its current location. This suggested one thing: Zeta Ophiuchi was thrown out. But thrown out by what? That question led to one of the most extraordinary realizations in modern stellar astronomy. The answer lies in its status as a runaway star, a rare class of stars that have been forcibly ejected from their original systems by powerful cosmic events. Zeta Ophiuchi had not just drifted, it had been launched. The galaxy is a vast place, but Zeta Ophiuchi's motion is like that of a high-speed traveler with a broken past. Imagine a star system, peacefully rotating, two massive stars orbiting one another in an intricate gravitational dance. One day, one of those stars reaches the end of its life and explodes as a supernova, unleashing an incomprehensible burst of energy. In an instant, the gravitational balance is shattered. The partner, Zeta Ophiuchi, is released from the system and flung into the galactic void at incredible speed. This is the fate Zeta endured. It didn't choose exile, it was sentenced to it. Now, as it tears through space, it doesn't carry planets or moons. It doesn't follow the rhythm of a cluster or return to the location of its birth. Instead, it roams fast and alone, its very presence a haunting reminder of the violence that sent it running. But this exile is not invisible. It leaves a trail. Zeta Ophiuchi's motion through the galaxy creates physical effects that astronomers can measure: disturbances in gas, light patterns, and radiation. All these signs tell the story of a star that once belonged, and was violently cast out. It is the embodiment of separation on a galactic scale. Not lost, but forcefully removed. There's a kind of poetic tragedy to this. Stars don't think or feel, but Zeta Ophiuchi is the kind of object that inspires the human imagination to wonder, what would it mean to be cast away from everything familiar, and to carry on shining regardless? To understand what makes Zeta Ophiuchi so extraordinary, we have to step back and ask, what exactly is a runaway star? On the surface, it may sound like a poetic name, like a wayward soul traversing the galaxy. But in astrophysics, the term carries specific and fascinating implications. A runaway star is not merely one that moves quickly through space. It is a star that has been violently and abruptly ejected from its birthplace or stellar system, often with speeds far exceeding those of stars around it. Most stars in the Milky Way, including our own Sun, orbit the center of the galaxy in relatively stable, predictable paths. Their motions are calm on cosmic timescales, shaped gradually by the gravitational pull of billions of stars and clouds of gas. But runaway stars are the exceptions. They move much faster than their neighbors, and they often travel on unusual trajectories that suggest something drastic changed their fate. There are two main ways a star can become a runaway: dynamical ejection and supernova disruption. The first, dynamical ejection, occurs in dense stellar environments such as young star clusters. In these chaotic regions, stars form in large groups, sometimes dozens or hundreds packed into a relatively small volume of space. In this kind of stellar crowd, close encounters are inevitable. When two binary star systems interact gravitationally, or when a single star comes too close to a binary pair, the intense gravitational interactions can sling one or more of the stars out of the cluster entirely. Think of it like a cosmic game of billiards, except the cue ball is gravity, and the stars are launched into the void. These kinds of ejections can happen early in a star's life, sending it out before it even has time to settle into its stellar neighborhood. The second mechanism, and the one more relevant to Zeta Ophiuchi, is far more violent. This is the supernova ejection scenario. In this case, a star forms in a binary system with a companion. These two stars orbit each other closely, locked in a gravitational dance that may last millions of years. But if one of those stars is significantly more massive, it will burn through its nuclear fuel faster and reach the end of its life sooner. That end, for massive stars, is a supernova explosion. When that explosion occurs, several things happen all at once. First, a tremendous amount of mass is ejected from the exploding star, sometimes more than half its total mass, creating an immediate and drastic change in the gravitational dynamics of the system. Second, the force of the blast itself may push against the companion star, delivering a shockwave of kinetic energy. Together, these effects unbind the binary system and send the surviving star flying outward at extraordinary speeds. In essence, the explosion acts like a slingshot, or perhaps a gun, and the companion becomes a runaway. What makes this all the more incredible is that stars are not light. They are massive, massive objects. To accelerate a star to runaway velocities, sometimes tens or even hundreds of kilometers per second, requires a tremendous release of energy. It's a process that only the universe's most violent events can supply. Not all runaway stars travel alone. Some of them, particularly in the dynamical ejection scenario, may retain a partner if they were ejected as a binary. Others, like Zeta Ophiuchi, become stellar loners, flung into space with no remaining companion, haunted by the echo of the explosion that changed their destiny. Interestingly, astronomers can identify runaway stars not only by their speed but also by the path they trace through space. By measuring their motion and velocity in 3 dimensions and calculating their trajectories backward through time, it's possible to determine where they came from, and often to identify whether they were part of a cluster or a binary system. Some have even been traced back to supernova remnants, linking them definitively to the death of a companion star. Runaway stars are more than just speedsters, they're messengers from the past. Their trajectories tell us about the environments they came from, the companions they lost, and the violence they endured. And as they blaze through the galaxy, they continue to shape the interstellar medium, heating gas, creating shockwaves, and contributing to the complex ecology of the cosmos. Zeta Ophiuchi is a textbook example of a runaway star, but as we'll see, it's also something more. Its sheer speed, mass, and the aftermath it leaves in space make it one of the most fascinating runaway stars ever studied. But to truly understand how it got here, we must turn to the explosion that set it free. The story of Zeta Ophiuchi cannot be told without delving into the violent final act of its companion star, a supernova, one of the most energetic and catastrophic events in the known universe. Supernovae are so powerful that, for a brief moment, a single star can outshine an entire galaxy. But for Zeta Ophiuchi, this wasn't a distant fireworks show. It was a close-range detonation that tore apart its cosmic reality and reshaped its fate. Zeta Ophiuchi was once part of a binary star system, a pairing of 2 stars orbiting a common center of mass. In such systems, especially when both stars are massive, their fates are tightly intertwined. The more massive of the 2 burns hotter and faster, exhausting its nuclear fuel more quickly. In the case of Zeta Ophiuchi, it was the less massive of the 2 at birth, though still significantly large by stellar standards. The companion star, even bigger, would have had a relatively short but intense life. Over time, the massive companion began its slow collapse. It likely went through the typical life stages of a high-mass star, burning hydrogen into helium in its core, then helium into heavier elements like carbon and oxygen, progressing layer by layer like an onion. But eventually, even this could not be sustained. Once iron formed in the core, nuclear fusion could no longer yield energy. At that point, the core collapsed under its own gravity in a fraction of a second, triggering the outer layers to explode outward in a cataclysmic blast. This was the moment everything changed for Zeta Ophiuchi. To grasp the scale of such an explosion, consider this: a core-collapsed supernova releases more energy in a few seconds than our Sun will emit in its entire 10 billion-year lifespan. The shockwave of radiation, neutrinos, and expelled stellar material blasted outward in all directions. If Zeta Ophiuchi had been just a little closer, it could have been destroyed or heavily stripped by this expanding wall of death. But instead, it survived, and that survival came at a cost. The system was no longer balanced. Before the explosion, both stars orbited a center of mass dictated by their mutual gravitational attraction. But when the companion star blew apart, a huge portion of its mass, perhaps more than half, was suddenly ejected into space. In a flash, the gravitational tether between the 2 stars was severed. Like a ball on a string being swung in a circle, if the string is cut mid-swing, the ball flies off tangentially. Zeta Ophiuchi was the ball, and the supernova cut the string. But there was more than just a loss of gravity. The supernova also delivered a mechanical kick. The asymmetries in the explosion, combined with the shockwave and the sudden unbinding of the system, gave Zeta Ophiuchi a blast of acceleration, launching it outward at tens of kilometers per second. The result? A high-velocity journey that would take it thousands of light years from the place it once called home. This event not only expelled Zeta Ophiuchi, but it also created a relic, or rather, left one behind. The exploded star didn't vanish entirely. Its collapsed core, stripped of its outer layers, likely became one of 2 things: a neutron star, or, if massive enough, a black hole. These are the dense, compact remnants that lie at the heart of every core-collapsed supernova. However, we haven't definitively detected this remnant. It could be hidden behind clouds of gas, or moving away in another direction, or simply too faint to observe. But its existence is almost certain. Astronomers studying Zeta Ophiuchi's motion have tried to trace its path backward. By calculating its current speed and trajectory, and projecting it in reverse, researchers have identified possible points of origin, and with them, potential sites of the original supernova explosion. The search continues for the corresponding supernova remnant, but the fact remains, Zeta's current velocity is too great, too directional, and too unaccounted for by galactic dynamics alone. Something gave it a push strong enough to overcome the gravitational pull of its original cluster or stellar nursery. And only an event as violent as a supernova could supply that kind of energy. The implications of this story go far beyond one star. Supernova ejections are a key mechanism by which stars are scattered across the galaxy. They play a role in redistributing elements, disturbing interstellar gas, and even influencing future star formation. The blast that launched Zeta Ophiuchi also seeded its surroundings with heavy elements forged in the heart of its companion, carbon, oxygen, iron, and more. These materials will eventually cool, collect, and perhaps one day become part of new stars, planets, or even life. What's especially profound is that Zeta Ophiuchi likely owes much of its current state to that very companion. Before the explosion, mass transfer may have occurred between the stars. In many massive binary systems, the more evolved star begins shedding its outer layers, and the material spirals onto the companion. This can make the recipient more massive, more luminous, and more turbulent than it would have been alone. So in a sense, Zeta Ophiuchi was not only kicked out by the supernova, it may have been transformed by its partner long before the explosion happened. The end of the companion was the beginning of Zeta Ophiuchi's journey as a runaway. A journey that continues to this day, millions of years later, as it races through the galaxy, carrying the memory of that violent separation imprinted in every photon it emits, every shockwave it creates, and every degree of heat it radiates into space. The legacy of that supernova is not just in the neutron star or black hole it may have left behind. It's in Zeta itself, a luminous survivor, propelled into the interstellar night by the death of its closest companion. Zeta Ophiuchi's story becomes even more remarkable when you consider just how fast it's moving. While stars generally orbit the center of the Milky Way at impressive speeds, our own Sun, for example, moves at about 220 kilometers per second in its galactic orbit. Those motions are orderly, curved, and slow to shift across the sky. But Zeta Ophiuchi isn't just participating in the grand rotation of the galaxy. It's been thrown onto a hyperkinetic, straight-line trajectory, carving a path that slices across the ordinary stellar backdrop. Zeta Ophiuchi is traveling at approximately 24 kilometers per second relative to its surrounding interstellar environment. On paper, this may seem modest. After all, spacecraft like the Parker Solar Probe can reach similar speeds. But remember, Zeta is not a human-made machine. It is a massive, searing ball of plasma, over 20 times the mass of the Sun and millions of times more difficult to accelerate. For something that large to move so quickly means that an immense amount of energy was involved in setting it into motion, far more than any propulsion system we've ever imagined. To visualize its speed, consider this. The average distance between the Earth and the Moon is about 384,000 kilometers. At 24 kilometers per second, Zeta Ophiuchi could hypothetically cover that distance in just 5 hours. That's faster than any human technology has traveled between the two worlds. And unlike a spacecraft that needs fuel, thrust, and course corrections, Zeta is gliding through the vacuum of space with no resistance and no slowing down, its velocity inherited from the catastrophic ejection event that changed its fate forever. But its movement isn't just a straight line through empty space. It's a supersonic tear through the interstellar medium. That 24 kilometers per second velocity isn't merely about travel from point A to point B. It's about how a blazing object interacts with its cosmic surroundings. The interstellar medium, while incredibly thin compared to Earth's atmosphere, still contains gas and dust. At such high speeds, Zeta Ophiuchi compresses and heats this material, generating shockwaves and turbulence. We'll explore that in greater depth later. But the takeaway is that this speed has real, visible consequences across light years. There's also the matter of trajectory. Thanks to precise astrometric data from missions like Hipparcos and Gaia, astronomers have been able to chart the three-dimensional path of Zeta Ophiuchi through the galaxy. They've reconstructed its past position and velocity, tracing it back to where it likely began, near a now dispersed stellar association, possibly the Upper Scorpius subgroup of the Scorpius, Centaurus OB association, a large collection of hot, young stars. That region is about 1 to 2 million years behind Zeta Ophiuchi in space and time, suggesting that this is where the original supernova took place. This high-precision motion data is a powerful tool. It allows researchers to piece together the timing of the supernova that launched Zeta Ophiuchi, giving us estimates not just of how fast it's moving, but how long it's been moving. Based on this data, it's likely that Zeta was ejected roughly 1 to 2 million years ago, a blink of an eye in cosmic terms, but enough time for the star to travel hundreds of light years from its point of origin. Its velocity relative to the galactic background also provides insight into stellar dynamics. In most parts of the galaxy, stars born in the same region drift apart slowly over hundreds of millions of years. Zeta's speed, however, means that it has dramatically outpaced its peers. If you were to observe a star cluster where Zeta once belonged, you might find stars gently separating from one another. But Zeta? It's long gone, like a race car that launched from the starting line before anyone else even turned the key. And that speed isn't just horizontal. Zeta Ophiuchi also exhibits a vertical component to its motion, meaning it's moving up or down relative to the galactic plane. This suggests its ejection wasn't confined to a simple orbit, it was a three-dimensional blast. It didn't just fall out of a circle, it was thrown out of the plane of the galaxy, potentially passing through different regions of density, radiation, and magnetic fields as it continues its lone voyage. Interestingly, not all runaway stars are so fast. Many travel at speeds of 10 kilometers per second or less, often resulting from more gentle interactions or gravitational nudges. But stars like Zeta, traveling at more than double that speed, are among the most extreme, the most energetic, and the most disruptive. This class of high-speed runaways tells us a great deal about the violent end stages of massive stars, and about the way binary systems can create forces strong enough to tear a stellar system apart. It's worth emphasizing again that Zeta Ophiuchi is not slowing down. In space, without friction or drag, an object in motion remains in motion unless acted upon by another force. And there's no significant force out there strong enough to halt or even meaningfully decelerate a star like Zeta. It's like a cosmic cannonball, coasting on momentum, likely for millions more years, until it either slows marginally due to galactic drag over tens of millions of years, collides with another object, highly unlikely, or ends its life in yet another cataclysm, its own supernova. There's also a fascinating implication here for the structure of the Milky Way. High-speed stars like Zeta help mix the stellar populations of the galaxy. By traveling far from where they formed, they distribute the chemical fingerprints of their birthplaces into new regions. As it travels, Zeta Ophiuchi carries the unique chemical markers of the Scorpius, Centaurus association, effectively pollinating other parts of the galaxy with the memory of its origin. In this way, runaway stars don't just move, they reshape the chemical and dynamic structure of the galaxy over time. In short, Zeta Ophiuchi's velocity isn't just a number, it's a message. A message about its past, a force of disruption in the present, and a promise of motion in the future. It's not just a star on the move, it's a star set in motion by violence, continuing to race through space with the quiet inertia of trauma, long after the blast that hurled it was extinguished. Zeta Ophiuchi's velocity and past make it extraordinary, but its very nature as a star is just as impressive. Not only is it fast, but it is also one of the most massive and luminous stars visible to the naked eye. When we look deeper into its identity, we find that Zeta Ophiuchi belongs to a rare and powerful class of stars, the O-type stars. These are the behemoths of the stellar population, stars that live fast, shine fiercely, and die young in dramatic explosions. Zeta Ophiuchi is no exception. Classified specifically as an O9.5V star, Zeta Ophiuchi sits at the cooler and less massive end of the O-type range, but don't let that fool you. Even among these rare giants, it commands attention. This single star contains more than 20 times the mass of our Sun, and it radiates with a luminosity that is over 65,000 times that of the Sun. That's not a typo. Zeta Ophiuchi is so radiant that it would make our Sun seem like a faint ember by comparison. Its power is a function of both mass and temperature, and Zeta Ophiuchi excels in both. O-type stars are known for their incredible surface temperatures, and Zeta Ophiuchi is no different. Its outer atmosphere burns at around 34,000 Kelvin, which gives it a piercing blue-white glow. This intense temperature also means that it emits the bulk of its radiation not in visible light, but in the ultraviolet range, invisible to the human eye but potent enough to ionize gas in nearby interstellar space. This radiation helps carve out regions of ionized hydrogen, known as H2 regions, and plays a major role in the life cycle of interstellar clouds. The energy output from such a massive star doesn't just radiate outward peacefully. It's accompanied by a powerful stellar wind, streams of charged particles being blasted away from the surface at high velocities. For Zeta Ophiuchi, this wind is traveling at thousands of kilometers per second, carrying away significant amounts of mass over time. These stellar winds help to shape the surrounding interstellar medium, create bow shocks, and drive shock waves through space that can even trigger the formation of new stars in nearby molecular clouds. We'll dive deeper into its bow shock soon, but it's important to note here that the strength of this stellar wind is directly tied to its classification and mass. Massive stars like Zeta Ophiuchi have very different life stories than stars like the Sun. Whereas our Sun will live for around 10 billion years, Zeta's massive core burns through its nuclear fuel at a furious pace. Its estimated lifespan is on the order of just 5 to 7 million years, and it's likely already lived more than half of that time. In fact, some models suggest it may be approaching the final few million years of its life before it ends in a spectacular core collapse supernova, possibly leaving behind a neutron star or black hole of its own. Its massive size also influences its internal structure. Unlike smaller stars, where energy is transported outward via a radiative core and a convective outer envelope, stars like Zeta have fully convective cores and radiative envelopes, which drastically alter how energy is moved and how the star evolves. The fusion in its core isn't limited to just hydrogen into helium either. As it ages, Zeta will begin fusing heavier and heavier elements, building up layers of different elements like concentric shells inside an onion. Each new fusion process is shorter-lived than the last, ending in iron, at which point the star can no longer sustain itself and collapses catastrophically. Another fascinating aspect of Zeta Ophiuchi is that its current mass may not reflect its original mass. Because it was once part of a binary system, there's a strong possibility that mass transfer occurred. In such scenarios, the more massive star, Zeta's now dead companion, would have expanded and shed mass onto its partner. That process may have made Zeta even more massive than it began, fundamentally altering its evolutionary trajectory. This complicates models of its future but also makes it an especially intriguing object of study for stellar evolution theorists. Its sheer brightness also makes it relatively easy to study, despite its distance. Sitting about 366 light-years away, Zeta Ophiuchi is still bright enough to be seen with the naked eye under dark skies. In fact, its apparent magnitude is around 2.5, making it one of the brighter stars in the Ophiuchus constellation. This accessibility has made it a frequent target for observational campaigns, especially in ultraviolet and infrared wavelengths, where its true power is revealed. And yet, despite its brilliance and size, Zeta Ophiuchi remains something of a quiet enigma. It's close enough for us to study in detail, but its rapid movement, complex wind environment, and hidden past make it difficult to fully unravel. Its classification as an 09.5 V star tells us it is still on the main sequence, meaning it is still fusing hydrogen into helium in its core. But with its massive fuel tank burning so hot, that phase won't last much longer. Eventually, it will evolve into a giant or supergiant, and then into a supernova, following in the tragic footsteps of its former companion. The rarity of O-type stars also makes Zeta Ophiuchi special. Despite their dominance in energy output, O-type stars are exceedingly rare. Only about 1 in every 3 million stars in the galaxy falls into this category. They contribute disproportionately to the brightness, structure, and chemical evolution of galaxies, yet they make up only a tiny fraction of the total stellar population. Zeta's visibility and proximity make it a valuable laboratory for studying these short-lived but powerful objects. In essence, Zeta Ophiuchi is a celestial powerhouse, burning hot, living fast, and destined to die young. It is not merely a fast star. It is a brilliant one, a massive one, and a star whose very light carries the fingerprints of its turbulent birth and uncertain destiny. Its classification, mass, and temperature are not just numbers. They are the coordinates of a life that has already been shaped by cataclysm, and will end in yet another. From our vantage point on Earth, Zeta Ophiuchi graces the celestial sphere in a place both ancient and rich in mythological significance. It resides within the constellation Ophiuchus, known as the Serpent Bearer, a lesser-known but deeply symbolic figure in the sky. This constellation, straddling the celestial equator, is home to many intriguing stars and deep sky objects, but few as captivating or dynamic as Zeta Ophiuchi. Ophiuchus lies between the better-known constellations of Scorpius and Hercules and is flanked by Sagittarius to the south. If you're observing from the northern hemisphere, especially in the summer months around June and July, you'll find Ophiuchus climbing high in the southern sky during the evening hours. Zeta Ophiuchi itself, with an apparent magnitude of about 2.5, is easily visible to the naked eye under dark skies, appearing as a bright bluish-white star amid a field of fainter companions. Despite its visibility, Zeta Ophiuchi doesn't draw the same attention as stars like Betelgeuse or Vega, perhaps because Ophiuchus is not one of the classical zodiac signs familiar to most casual stargazers. However, technically speaking, the Sun does pass through Ophiuchus during its apparent journey along the ecliptic. For roughly 18 days in late November and early December, the Sun moves through this 13th zodiacal constellation, though it's not officially part of the modern astrological calendar. Ironically, this adds a layer of hidden significance to Zeta Ophiuchi. It's one of the brightest stars in a constellation that many people don't even realize lies along the zodiac path. Located at right ascension 16 hours 37 minutes and declination -10 degrees 34 minutes, Zeta Ophiuchi sits roughly in the center of the Ophiuchus constellation, just above the tail of Scorpius when viewed in the night sky. This positioning makes it relatively easy to spot for experienced observers, especially those using star charts or astronomy apps. Its blue-white hue stands out distinctly, offering a visual clue to its temperature and spectral type, even for those without a telescope. In terms of cosmic distance, Zeta Ophiuchi is approximately 366 light-years away, a distance confirmed with increasing precision thanks to the astrometric measurements from ESA's Gaia mission. To put that in perspective, the light we see from Zeta tonight began its journey during the early medieval period here on Earth, roughly around the year 659 AD. In that time, entire civilizations have risen and fallen, and yet Zeta has continued to burn with relentless brilliance, moving ever farther from its original birthplace. That distance, 366 light-years, places it well within the local neighborhood of our galaxy, but far enough that it's not affected by the day-to-day motions of the solar system. And yet, given its incredible velocity, Zeta Ophiuchi doesn't just passively hang in the sky. It's been shifting position relative to background stars over decades and centuries. Careful measurements of proper motion, the change in a star's position on the sky, reveal that Zeta is not stationary. It's plowing across the heavens, and that movement gives us direct insight into the forces that expelled it from its original home. Astronomers can use its current position, velocity, and direction to trace its path backward across the sky. That forensic reconstruction suggests that Zeta Ophiuchi once belonged to a nearby stellar association, possibly the Upper Scorpius subgroup within the larger Scorpius, Centaurus OB association. This region, rich in young, massive stars, is known as a stellar nursery, and it would have been the perfect birthplace for Zeta and its now-dead binary companion. The fact that Zeta is now hundreds of light-years away from this region, and still racing farther, makes its location in the sky a kind of celestial crime scene. The star's current coordinates are not a place of origin, but a snapshot in motion. Its visibility and location also make Zeta Ophiuchi a key object of study across multiple wavelengths. Being relatively close to Earth, it provides astronomers with an excellent laboratory for understanding high-mass stars and their interactions with the interstellar medium. Observatories on Earth and in space have turned their instruments toward this star again and again, from optical telescopes measuring its spectral lines to infrared observatories like Spitzer, which captured the shock structures it generates as it tears through space. The space around Zeta Ophiuchi is far from empty. The star is currently located within a region that contains a significant amount of interstellar gas and dust, and its motion through this medium generates some of the most fascinating phenomena associated with runaway stars, most notably the bow shock, which we'll explore shortly. This interaction between the star and its environment is ongoing and visible, providing a living snapshot of astrophysical processes in action. Its place in the sky also allows for long-term monitoring. Unlike stars located in heavily obscured regions of the Milky Way or deep within dense clusters, Zeta Ophiuchi is relatively isolated and unobscured, making it ideal for time series observations. Astronomers have been able to track its changes in brightness, spectral variability, and even X-ray emissions, all from a clear vantage point. There's a kind of irony in its position. Despite being a brilliant and massive star, Zeta Ophiuchi lies within a constellation that most people have never heard of, in a zodiacal path that astrology doesn't acknowledge. It's a bright beacon in an underappreciated region of the sky, a hidden giant, both figuratively and literally. Its cosmic isolation mirrors its physical reality, cast out, alone, and racing away from its origins, yet burning brightly for all to see, if they know where to look. In the end, Zeta Ophiuchi's location is not just a set of coordinates, it's a cosmic waypoint, a stop along a vast, lonely journey through the galaxy. It marks a chapter in a story that began with formation and partnership, was torn apart by destruction, and now unfolds as a high-speed odyssey across the stars. From our small blue planet, we watch it pass by, one of the most brilliant stars in a quiet, overlooked corner of the sky. One of the most visually striking and scientifically revealing features of Zeta Ophiuchi's interstellar journey is the bow shock that stretches out ahead of it like a glowing cosmic crest. It's not something you can see with the naked eye, but in the right wavelengths, particularly in the infrared, it becomes a brilliant arc of compressed, energized gas and dust. This structure is more than just beautiful, it's a dynamic footprint of stellar motion, sculpted by supersonic speeds, stellar winds, and the resistance of the interstellar medium. And in Zeta Ophiuchi's case, this bow shock is among the most well-defined and widely studied in the galaxy. To understand how a bow shock forms, imagine a speedboat racing across a still lake. As it pushes forward, the hull of the boat displaces water, creating ripples that curl outward in a V-shape. Now translate that same concept into space. Zeta Ophiuchi is the boat, and the interstellar medium, the sparse mix of gas, dust, and plasma that permeates the galaxy, is the water. But instead of liquid, it's made up of particles like hydrogen atoms, electrons, and microscopic grains of cosmic dust. And instead of ripples, we get a shockwave, a boundary layer where gas is heated, compressed, and energized by the star's passage. Zeta Ophiuchi's movement through space is supersonic relative to this interstellar material. That means it's moving faster than the speed at which sound waves, or more accurately, pressure waves, can travel through the gas ahead of it. As a result, particles and magnetic fields pile up and compress at the front of the star's motion, forming a curved shock front that glows when observed in certain wavelengths. This is the bow shock, and it's not just a pretty halo. It's an active, evolving structure that provides rich data about the physics of stellar winds, gas dynamics, and interstellar interaction. What makes Zeta Ophiuchi's bow shock especially compelling is its clarity and size. It extends several light-years ahead of the star, forming a wide, arcing structure that envelopes the forward motion of the stellar wind. Observations from NASA's Spitzer Space Telescope captured this bow shock in incredible detail in the infrared spectrum, revealing a curved wave of bright, warm dust glowing in response to the pressure and radiation from Zeta's powerful stellar wind. That stellar wind is essential to the process. Like all O-type stars, Zeta Ophiuchi emits a constant stream of high-energy particles from its surface, driven by radiation pressure from deep within its interior. These winds travel outward at thousands of kilometers per second, colliding with the interstellar gas in front of the star and pushing it aside like a snowplow through fresh powder. But because Zeta is moving so fast through the medium, the collision isn't gentle, it's explosive. The result is a shockwave that compresses the gas to extreme densities, heating it to temperatures of tens of thousands of degrees and causing it to emit radiation in infrared and even some optical bands. The shape of the bow shock tells us a lot. It's typically parabolic or crescent-shaped, with the apex, or nose, pointing in the direction of the star's motion. The symmetry of the shock reveals the relative uniformity of the interstellar medium, while any irregularities or warps in the structure can suggest regions of higher density or magnetic field interference. For Zeta Ophiuchi, the bow shock is smooth and well-defined, indicating that it's moving through a relatively homogeneous region of space. But even so, ripples and subtle curves in the arc provide clues about density fluctuations and interstellar turbulence. This is not just a passive structure. The physics of the bow shock involves a complex interplay between the star's velocity, the density of the interstellar gas, the temperature and pressure gradients, and magnetic field lines that may stretch across space like invisible wires. Models that simulate Zeta Ophiuchi's motion take into account all these factors, and astrophysicists use the real-time shape of the shock to refine their understanding of supersonic astrophysical objects. Interestingly, these shocks may also be cosmic accelerators. In regions of extreme pressure and magnetic distortion, particles can be accelerated to high energies, similar to the mechanisms at work in the Earth's magnetosphere or in the remnants of supernovae. While Zeta's bow shock doesn't reach the same energy levels as those associated with pulsars or black holes, it may still contribute to local cosmic ray populations, adding a subtle but measurable effect to the environment it passes through. From a broader perspective, Zeta Ophiuchi's bow shock is a moving laboratory. It allows astronomers to study how massive stars interact with their environment, not just in their own lifetime, but in ways that shape the galaxy. The compression of interstellar gas ahead of the shock can trigger star formation, especially if the shockwave presses into a nearby molecular cloud. In this way, Zeta Ophiuchi isn't just a traveler, it's an agent of change, stirring the cosmic soup it crosses, reshaping the densities and pressures that eventually birth new stars and planetary systems. The bow shock also tells us a great deal about stellar wind dynamics. By comparing the position and brightness of the shock to theoretical models, astronomers can calculate the mass loss rate of Zeta Ophiuchi. That is, they can estimate how much mass the star is shedding every year due to its powerful winds. For a star like Zeta, this can amount to billions of tons per second, slowly peeling away its outer layers long before its eventual demise as a supernova. Over time, this mass loss can significantly alter the star's evolution, reducing its mass and luminosity, and changing the composition of its outer layers. Beyond the scientific value, there's something deeply aesthetic about the image of a bow shock. It's not merely a byproduct of motion, it's a symbol of struggle and resistance. Zeta Ophiuchi isn't gliding silently through a vacuum. It's battling its way across the cosmos, pushing against the invisible substance of interstellar space, forcing it to bend and heat and glow in response. The bow shock is a scar of motion, a visible testament to the star's velocity, history, and strength. And this glowing arc isn't permanent. As Zeta Ophiuchi continues its journey, the density of the interstellar medium may change, altering the size, shape, or even visibility of the bow shock. If it enters a region with significantly lower gas density, the bow shock may fade. If it crosses a dense cloud, the structure could flare into new brilliance or warp unpredictably. In this way, the bow shock is a living record of the star's interactions, constantly rewritten by the medium it travels through. In sum, the bow shock is not just a curious feature, it is the signature of Zeta Ophiuchi's exile. It marks the front line where this stellar fugitive confronts the resistance of the galaxy. Like a comet's tail pointing to the sun, the bow shock points to Zeta's path through time and space, illuminating not just where the star is, but where it has been, and where it's going. The bow shock surrounding Zeta Ophiuchi may be invisible to human eyes, but when seen through the lens of infrared astronomy, it becomes a glowing, sculpted testament to the power and speed of this runaway star. The Ballistic's ethereal beauty was most famously captured by NASA's Spitzer space telescope, a powerful observatory that spent over 16 years mapping the universe in infrared wavelengths. In Spitzer's view, the hidden violence and subtle structure surrounding Zeta Ophiuchi were unveiled with breathtaking clarity, transforming a simple stellar motion into a majestic cosmic display. Infrared light allows astronomers to pierce through the murky veils of interstellar dust and gas that obscure many objects in visible light. It reveals warm regions where matter is being energized, not necessarily heated to scorching temperatures, but excited enough to emit infrared radiation. Zeta Ophiuchi's Ballistic is one of those regions. As the star plows through the interstellar medium at supersonic speeds, its stellar wind rams into surrounding gas and dust, compressing and heating it just enough to make it glow in the infrared spectrum. To Spitzer, this was a signal not of chaos, but of structure, a glowing arc that curves ahead of the star like a celestial wave crest. In the Spitzer image, the star itself appears as a bright blue-white dot at the base of a curved, flame-like arc. That arc is the Ballistic, a ripple of red, orange, and yellow hues sculpted by the motion of Zeta Ophiuchi. The false colors in the image represent different infrared wavelengths, carefully processed to highlight the contrast between the background sky and the dust energized by the Ballistic. The result is more than just scientifically useful, it's visually stunning, an artwork forged by physics and time. But this beauty is more than skin deep. The Spitzer observations provided scientists with critical quantitative data. By analyzing the brightness, temperature, and extent of the infrared glow, astronomers could estimate key properties of the Ballistic: the density of the interstellar medium, the speed and mass loss rate of the stellar wind, and the energy transfer taking place at the shock boundary. These measurements confirmed what theory had long suggested, that Zeta Ophiuchi's speed and wind strength are more than enough to carve out this massive structure, even in the thin gas between stars. One of the most fascinating discoveries was just how far ahead of the star the Ballistic extends. In Spitzer's view, the apex of the arc lies roughly a third of a light-year ahead of the star, a distance of trillions of kilometers. This tells us how much time and space it takes for the stellar wind to slow down and compress into the shape we see. The standoff distance, the space between the star and the shock front, is a direct result of the balance between the pressure of the stellar wind and the pressure of the interstellar gas. The stronger the wind or the thinner the medium, the farther out the shock front will form. What Spitzer's image also captured, indirectly, was the asymmetry of the environment. Though the arc appears fairly symmetrical, there are subtle differences in brightness and shape along its length. These reveal variations in the density of the interstellar medium or changes in the magnetic field structure that Zeta Ophiuchi is plowing through. Such asymmetries help refine our models of galactic gas distribution, shedding light on how diffuse matter is arranged even across regions that appear empty to the eye. And Spitzer wasn't alone in admiring Zeta Ophiuchi. Other infrared observatories, including WISE, the Wide Field Infrared Survey Explorer, have also captured images of the star and its shockwave, confirming and complementing Spitzer's results. These surveys help track how the structure evolves over time, allowing astronomers to test simulations of Ballistic physics and refine the physical parameters that govern such systems. With repeated observations, it's possible to monitor changes in brightness, slight movements of the arc, or even new substructures that form as the star enters denser or more magnetized regions of the galaxy. Spitzer's contribution was especially important because it filled a crucial observational gap. Optical telescopes can't see Ballistics like Zetas. There's simply too much obscuring material, and the shock doesn't emit much visible light. Meanwhile, radio telescopes can trace large-scale gas structures, but with far less detail. Infrared, however, is the sweet spot for Ballistics, sensitive enough to see warm dust, and sharp enough to trace arcs, filaments, and waves in exquisite detail. And with Zeta Ophiuchi located a manageable 366 light-years away, Spitzer's detectors were able to provide some of the clearest images of a Ballistic ever taken. What's more, these images have had impact beyond astrophysics. The dramatic visual of Zeta Ophiuchi's Ballistic has been used in educational materials, planetarium shows, and science outreach around the world. It is often highlighted as a prime example of how infrared astronomy reveals hidden phenomena, unseen forces shaping the universe that become visible only when we look beyond the narrow range of human sight. Perhaps most poetically, Spitzer's image of Zeta Ophiuchi reminds us of how stars leave scars on the universe. The bow shock is not part of Zeta's original body. It is not something born with the star. It is a wound carved into the galaxy by motion, by force, by exile. It tells a story of energy violently unleashed and still rippling outward. Through infrared eyes, we see the aftershocks of a cosmic trauma, not just a star moving, but a star that has been launched, forced to push against the invisible tides of space with such intensity that even the dust recoils in light. And though Spitzer has since been retired, its legacy lives on in images like this. The mission may have ended, but the data remains, a frozen snapshot of a star in flight, still illuminating the space ahead with waves of heat and light. Zeta Ophiuchi continues to speed onward, but thanks to Spitzer, we caught it in the act, a celestial fugitive, wrapped in infrared flame, forever marked by the violence that sent it on its way. As Zeta Ophiuchi charges forward through space at supersonic speeds, the interstellar medium doesn't just compress and glow in front of it, it is also profoundly disturbed behind it. Like a speedboat racing through a still lake, Zeta leaves behind a roiling wake, a chaotic, stretched-out trail of disturbed gas and dust. This interstellar wake is an essential counterpart to its bow shock, a turbulent signature that traces not just where the star is going, but where it's been, what it's passed through, and how it has reshaped the galactic medium in its path. This wake, largely invisible in visible light, becomes evident in infrared, radio, and far ultraviolet wavelengths. Observations from missions like Spitzer, WISE, and the Herschel Space Observatory have captured subtle traces of dust and gas that have been churned up, compressed, and dragged along in the star's trail. This turbulent region can stretch for several light years, an elongated ghost of the star's past, shimmering faintly in the residual heat and scattered light it leaves behind. At its core, the interstellar wake is caused by the same mechanics that form the bow shock. Zeta Ophiuchi's powerful stellar wind, rich in ionized particles and moving at thousands of kilometers per second, doesn't just push forward, it also expands outward and interacts with the interstellar medium around it in every direction. As the star moves forward, material it once influenced becomes displaced, stirred, and stretched into a turbulent flow. The wake is essentially the region of shocked, warmed material left behind by the passage of both the stellar wind and the star itself. The shape of the wake depends heavily on the properties of the surrounding medium. In denser regions, more material gets swept up and the wake becomes brighter and more structured. In lower density zones, the wake can become diffuse and difficult to detect. But in all cases, the wake is not uniform. It's filled with eddies, clumps, and filaments, signatures of instabilities caused by differential motion, magnetic fields, and thermal gradients. These instabilities are similar to those that form when you blow smoke through air or drag your fingers through water, turbulent, shifting, and complex. One of the most fascinating aspects of the wake is that it carries chemical fingerprints of the star. The interstellar medium is not a static sea, it's an evolving mixture of hydrogen, helium, metals, and dust grains. As Zeta Ophiuchi travels through it, it injects freshly produced elements, especially carbon, nitrogen, and oxygen, into its wake via its stellar wind. This enriched material becomes part of the galactic ecology, spreading heavier elements into regions that might one day collapse to form new stars and planets. In this sense, Zeta's wake is not just a disturbance, it's a trail of life-giving material, the seeds of future generations of stars. Moreover, the wake serves as a dynamical footprint that helps astronomers map the path of the runaway star. By observing the orientation, length, and brightness of the wake, scientists can determine the angle of motion, the velocity vector, and even past density conditions of the interstellar medium. A bright, compact wake may suggest the star recently passed through a denser region. A long, faint one might imply a more prolonged journey through a lower density zone. In some cases, particularly where magnetic fields are involved, the wake can also become polarized. Observations of polarized light from dust grains aligned by magnetic fields in Zeta's trail can reveal the magnetohydrodynamic behavior of the gas, the way plasma interacts with galactic magnetic lines. This is valuable not just for studying Zeta itself, but for probing the structure of the galaxy's magnetic field, a force that remains largely mysterious but essential in shaping galactic dynamics. It's also possible that shock waves from the wake could have secondary effects. Just as the bow shock compresses gas ahead of the star, the trailing wake could leave pockets of compressed material in its path. These denser clumps may, under the right conditions, become seeds of star formation, especially if they pass through nearby cold molecular clouds. Though speculative in Zeta's specific case, this is a known mechanism elsewhere in the galaxy, stellar feedback that jumpstarts new stellar bursts long after the original star has passed by. Another fascinating feature that has emerged from simulations of runaway stars like Zeta Ophiuchi is the potential formation of trailing vortices, large, swirling patterns of gas caused by shear flows in the wake. These vortices can persist for thousands of years, drifting slowly through space like cosmic whirlpools, trapping dust and influencing the thermal balance of their environment. Detecting these in the real galaxy is challenging, but their presence in detailed 3D models of bow shock systems adds another layer of dynamism to Zeta's interstellar impact. And yet this wake, rich in structure, movement, and consequence, is impermanent. As the star moves farther, its older trails begin to fade and disperse, blending back into the galactic background. The particles cool, the turbulence dies down, and the chemical traces become diluted in the vastness of the interstellar medium. Eventually, the wake may vanish entirely, leaving behind only subtle changes in the local composition and structure, a memory of passage, written in atomic abundances and dust alignment. But while it lasts, the wake is one of Zeta Ophiuchi's most eloquent messages to the universe. It's not a quiet crossing, it's a roar, a scratch across the fabric of space, a disruption that reverberates behind it for light years. The bow shock may point the way forward, but the wake tells us what's already been endured, where the star came from, what it passed through, and how it refused to go unnoticed. In every way, the interstellar wake is the signature of a cosmic rebel. It's not the path of least resistance, it's the trail of resistance overcome. Behind Zeta Ophiuchi, space is not as it was before. It is warmer, more turbulent, more enriched, more disturbed. And in that disruption, in that plume of star-carved chaos, we glimpse the force of motion, the memory of catastrophe, and the evidence of a star not merely in flight, but on a mission through the galaxy. The story of Zeta Ophiuchi is not one of gentle starlight or quiet cosmic drift, it is a narrative of trauma, force, and survival. Beneath its blazing brilliance and turbulent wake lie clues, forensic traces of a violent past, that tell us this star was once part of something more, something that ended in explosive tragedy. The clues are etched in its extreme velocity, illuminated in the arc of its bow shock, and hidden in the physics of its stellar wind and movement. Like a cosmic crime scene, these signs point toward a singular, catastrophic event, the supernova explosion of its binary companion. The most obvious evidence is its unusual speed. Zeta Ophiuchi races through the galaxy at nearly 24 kilometers per second, far faster than most stars in its neighborhood. This kind of speed is not arbitrary. It cannot be explained by the gravitational drift of normal stellar evolution. It's not the motion of a star casually orbiting the galactic center, it's the trajectory of an object that's been kicked, violently ejected from its original home. This sudden, high-velocity launch suggests an origin involving a massive, energetic event, specifically, a supernova. Runaway stars like Zeta Ophiuchi don't achieve their speeds without help. There are two known mechanisms that can launch a star like a bullet: dynamical ejection and supernova disruption. In the former, close gravitational encounters within dense star clusters can slingshot a star outward. But Zeta's path, traced backward through space using precise astrometric data from observatories like Gaia, doesn't lead back to a dense cluster. Instead, it points toward the Upper Scorpius-Ob association, a region filled with massive, short-lived stars, a prime breeding ground for binaries. This fact alone supports the second mechanism, the supernova of a binary companion. This narrative gains further support from the presence of a well-formed bow shock. As discussed earlier, Zeta Ophiuchi's supersonic motion through the interstellar medium has generated a clear arc of compressed gas ahead of it. But this isn't just a beautiful side effect, it's direct evidence of its exceptional speed. Stars moving at average galactic velocities do not create bow shocks of this magnitude. The presence of such a distinct structure confirms that Zeta is not merely drifting through space, it is tearing through it, a star on the run. The sharpness and symmetry of the bow shock reinforce the idea that this motion is the result of a sudden and powerful push. But the clues go deeper still. The nature of Zeta Ophiuchi itself provides forensic fingerprints of its past. It is a massive O-type star, and such stars often form in binary systems, particularly with other massive stars. Binary evolution models suggest that these stellar partnerships are not just common but critical to the evolution of high-mass stars. In these systems, mass can flow from one star to the other, dramatically altering their lifespans and fates. Zeta's high mass and youthful appearance for its inferred age suggest it may have accreted material from its now-dead companion, effectively being rejuvenated by this mass transfer. This process is known as mass stripping or mass accretion rejuvenation, and it is another signature of a binary origin. So, what might have happened? In its early life, Zeta Ophiuchi likely orbited a more massive star, one that evolved faster, burned through its nuclear fuel in a few million years, and reached the point of collapse. As that primary star neared the end of its life, it expanded into a red supergiant, possibly transferring mass to Zeta. Eventually, its core could no longer support itself. In a flash lasting seconds, it collapsed into a neutron star, or perhaps a black hole, releasing an enormous amount of energy in a supernova explosion. In the instant that explosion occurred, the balance that had kept the binary system together was shattered. A supernova doesn't just create light and shockwaves, it creates asymmetry and momentum. If the explosion is even slightly uneven, which most are, the resulting blast can impart a kick to the remaining objects. The dying star collapses, ejecting its outer layers outward in a sphere of high-speed plasma and radiation. The system's gravitational grip is broken. If the mass loss is rapid and substantial, which it would be, the remaining companion, in this case Zeta Ophiuchi, is flung outward, no longer bound to its partner. And if the binary orbit was tight, as simulations suggest Zeta's likely was, the resulting velocity can be immense. This ejection is not just theoretical. It's supported by Zeta's speed, direction, and isolation. It is no longer gravitationally tied to a cluster or companion. Its path through the galaxy is ballistic, a straight line of escape from an explosion long past. Astronomers call this class of stars runaway stars, and Zeta is one of the most prominent examples. But we also see the aftermath in what's not there. Zeta Ophiuchi has no visible companion today. If its partner had survived as a neutron star or black hole, it might still be nearby. Yet no such object has been definitively found, suggesting one of two possibilities. Either the remnant was flung in the opposite direction during the explosion and is now too far or faint to detect, or it was completely destroyed, torn apart in an especially violent collapse. Either scenario adds more weight to the explosive origin story. Even now, Zeta's trajectory is still being refined. The Gaia spacecraft is providing ever more precise measurements of its motion and parallax, allowing astronomers to reverse engineer its path through space. These models increasingly confirm that Zeta did not originate where we see it today, but rather was expelled from a region some hundreds of light years behind, likely the very location where its companion exploded. In every way, the evidence converges. The high velocity, the isolated position, the massive, luminous nature of the star, the well-defined bow shock, the absence of a visible companion, the alignment with a region of recent star formation. These are the hallmarks of a supernova survivor, a star that lived through the death of its partner and emerged not unscathed, but irrevocably changed. Zeta Ophiuchi is not merely a star in motion. It is a cosmic witness to a stellar death. The explosion that propelled it into this solitary path may be long past, but the clues are everywhere, encoded in gas, dust, velocity, and spectrum. And in decoding those clues, astronomers are not only uncovering Zeta's history, they are also piecing together the lives and deaths of the most massive stars in the galaxy, stars whose ends are often as spectacular as their beginnings. The fate of Zeta Ophiuchi's former companion is one of the most intriguing mysteries in its story, a cosmic, missing person, case with profound implications. This companion wasn't just a background star in its early life. It played a central role in Zeta's formation, evolution, and eventual exile. And yet today, it is nowhere to be seen. The star that once danced alongside Zeta, exchanging mass and gravity, has vanished without a trace visible to conventional telescopes. What happened to it? The answer, based on physics, models, and what we observe, or don't observe, likely falls into one of three dramatic scenarios. It became a neutron star, collapsed into a black hole, or was completely obliterated during the supernova event. Let's begin with the most conservative outcome, that the companion collapsed into a neutron star. This is the typical fate for stars that start out with around 8 to 20 times the mass of our Sun. These stars exhaust their nuclear fuel relatively quickly, within a few million years, causing their cores to collapse under their own immense gravity. The outer layers explode outward in a supernova, while the core condenses into a sphere of degenerate matter no larger than a city, but with a mass exceeding that of our Sun. If this is what happened, then Zeta Ophiuchi's companion may still exist somewhere, hidden in the galactic dark, speeding away in the opposite direction. But neutron stars, while small, are not invisible. They can often be detected in several ways. If they rotate rapidly, they can emit beams of radio waves or X-rays, becoming visible as pulsars. If they still have a remnant disk of matter around them, they might glow in X-rays as material falls in. Yet, despite extensive searches in the sky around Zeta Ophiuchi's projected trajectory, no pulsar or neutron star has been found. This could mean the companion is simply too faint, not emitting strongly in our direction, or too far away by now. Given the speed at which both stars may have separated, it's entirely possible the remnant is now hundreds of light years away, just another point of darkness in the vast cosmic sea. Another, even more dramatic possibility is that the companion collapsed into a black hole. If the progenitor star was more massive, perhaps 25 to 40 solar masses, it may have been massive enough that its collapsing core continued all the way down into a singularity, bypassing the neutron star stage. Black holes, of course, are invisible unless they are actively feeding on nearby material. If the remnant black hole was ejected into empty space, away from stars or gas clouds, it could be essentially undetectable. In this scenario, Zeta's companion still exists, but has entered the quietest state a star can achieve, a gravitational ghost, leaving no light, no signals, only a persistent absence. And yet there's a third possibility, one that's arguably even more violent. It's possible the supernova event was so energetic and asymmetric that it completely unbound and destroyed the companion star, leaving no remnant at all. While this is less common, simulations have shown that under certain conditions, particularly in close binary systems with extreme mass loss or rapid rotation, the explosion can completely disrupt the collapsing core, scattering it into space. If this happened, Zeta's partner didn't survive in any form. It ended in a catastrophic disintegration, a stellar self-annihilation that left Zeta alone in a streak of light. There's a haunting elegance in this idea, that Zeta was not just expelled from a partnership, but survived the destruction of its closest stellar companion, the way a single leaf might remain floating after a forest fire. This total loss scenario could also help explain why no remnant has ever been detected. If there's nothing left, no neutron star, no black hole, then the trail ends with Zeta, the last living memory of the binary that once was. Of course, there's still the possibility that the companion remnant does exist but has simply escaped detection. The sky is vast, and black holes or neutron stars without emissions are notoriously hard to spot. It might require gravitational lensing events, more sensitive X-ray surveys, or future all-sky radio arrays to uncover the final fate of this vanished star. Projects like LISA, Laser Interferometer Space Antenna, which aims to detect gravitational waves from compact objects, or Gaia, which might eventually spot the gravitational influence of unseen masses, could someday provide clues to the companion's fate. Interestingly, tracing Zeta Ophiuchi's motion backward through the galaxy offers some circumstantial evidence. When models account for its current speed and direction, they point back to the Upper Scorpius region, a well-known stellar nursery filled with massive stars and active star formation. This region is estimated to be around 5 million years old, perfectly in line with the age Zeta Ophiuchi would need to have formed in a binary, lived with its companion through early mass transfer, and then been expelled during a supernova that occurred roughly 1 to 2 million years ago. If we could match this timing with a known neutron star or black hole speeding in the opposite direction, we might finally pair the surviving halves of a broken stellar system. For now, though, the companion remains a missing link, its absence adding to the enigma of Zeta Ophiuchi. It's a silent question mark in an otherwise dramatic tale. But even in that absence, we find meaning. The very fact that Zeta is alone, moving with such speed, surrounded by a glowing bow shock, with no visible partner, speaks volumes about what occurred. It tells a story not just of companionship, but of violence, separation, and survival. And in the vastness of space, sometimes silence is the loudest evidence of all. So what happened to the companion? It was likely once a bright, massive star, bound to Zeta in a tight, burning orbit. Then, in an instant, it detonated, leaving behind either a collapsed core racing in the opposite direction, a black hole slipping silently through the galaxy, or nothing at all. Zeta's current speed, direction, and luminosity are the only surviving witnesses to that ancient stellar death. Zeta Ophiuchi's story didn't begin in isolation. Like the majority of massive stars in our galaxy, it was born in a binary system, tethered from the very start to another giant of nuclear fire. This isn't unusual. In fact, it's the norm for massive stars. Studies have shown that more than 70% of O-type stars, like Zeta Ophiuchi, are born in binary or even multiple star systems. But Zeta's case is a particularly dramatic example of what can happen when that early cosmic companionship is forged under intense gravitational pressure and ultimately ripped apart by the violent end of one of the stars. When we speak of stars being born, we're referring to their formation from collapsing clouds of gas and dust, stellar nurseries. In the case of Zeta Ophiuchi, this nursery was likely a part of the Upper Scorpius OB Association, a nearby stellar birthplace teeming with massive, short-lived stars. Within these regions, stars don't form alone. The collapsing clouds fragment under gravity, forming binary or multiple stellar embryos within the same region. These stars then grow by accreting material from their surroundings, their mutual gravity locking them into orbits around one another. Zeta's mass, over 20 times that of the Sun, means it had to form fast. Massive stars burn hot and bright, using up their fuel at an astonishing rate. To reach this size in just a few million years, Zeta would have drawn in large amounts of mass from its surrounding environment, likely with the help of gravitational interactions with its binary partner. From the beginning, this wasn't a passive relationship. Binary stars influence each other's growth, evolution, and eventual fate. The companion star, larger and more massive based on what we infer, would have evolved even more rapidly. In massive binaries, the more massive star enters the supergiant phase first, inflating and possibly even transferring mass to its companion. This mass transfer is a critical point in binary evolution. As the primary star swells up, its outer layers can spill over onto the secondary star, in this case, Zeta Ophiuchi. This changes both stars. The primary loses mass, which can actually prolong its life slightly, while the secondary gains mass, increasing its luminosity and altering its evolutionary track. Zeta Ophiuchi may have originally been the less massive of the pair. The transfer of matter from its companion would have caused it to increase in mass and brightness, becoming the O-type star we see today. This rejuvenation process is common in close binary systems and may even disguise a star's true age. Although Zeta appears young and hot, it may have had a more complex journey to that state, absorbing not just matter but also angular momentum, potentially spinning faster and generating stronger magnetic fields than it would have on its own. The orbit in such a system would have been tight and intimate, perhaps with a period of only a few days or weeks. These stars would have danced in gravitational lockstep, each shaping the other's fate. Their powerful winds, intense radiation, and tidal forces would have interacted constantly. And yet, as massive stars, both were doomed to short lives. The larger star, the original primary, would have burned through its nuclear fuel in only a few million years before collapsing in a core-collapse supernova, shattering the delicate gravitational balance that held the pair together. This is the tragedy of binary systems among massive stars. While they are born together, they rarely die together. One always evolves faster, often ending in violent collapse, while the other, if it survives, is flung into space, changed forever by the loss of its partner. Zeta Ophiuchi's ejection is not just the result of the explosion, but of the entire evolutionary journey the pair shared. Every stage of that early binary life shaped what Zeta would become, its mass, luminosity, wind strength, and even its ultimate trajectory through space. What remains today is a solitary star, but not one that was always alone. Every photon that leaves Zeta's surface, every shockwave it pushes into the interstellar medium, is a legacy of its binary origin. The mass it gained, the velocity it was given, the isolation it now endures, all are consequences of a long-lost partner whose presence was once as crucial to Zeta's identity as the hydrogen burning in its core. And while Zeta now appears to race independently through the galaxy, its bow shock, velocity, and the scars of gravitational memory all point back to that early companionship. Astronomers can read those scars, using spectral analysis, stellar models, and motion tracking to reconstruct a history that began not with one, but with two stars, entwined in mutual formation and separated by the most violent process in stellar evolution. In many ways, Zeta Ophiuchi is a stellar orphan. But it's also something more profound, a survivor. It is a living relic of a once powerful binary, a star that has lived on to tell the story that its companion no longer can. And in its light, in its motion, in the turbulence it stirs across the galaxy, that story continues to unfold, echoing through space not in words, but in velocity, brilliance, and the trail it leaves behind. Before Zeta Ophiuchi became the stellar fugitive we know today, before its bow shock blazed across the interstellar medium and before its high-speed journey through space began, it lived a very different life. In the stillness of its youth, Zeta was part of a tightly bound binary system, orbiting its massive companion in a delicate yet powerful gravitational dance. This was not a quiet companionship. It was a relationship defined by immense forces, searing temperatures, intense radiation, tidal interactions, and eventually, the transfer of mass and momentum that would reshape both stars forever. This pre-ejection phase was a period of intense stellar activity. Both stars were massive, likely more than 15 solar masses for Zeta and possibly 25 or more for its companion. In massive binary systems like this, evolution happens quickly. Within just a few million years of their birth, the larger of the two begins to exhaust the hydrogen in its core. It expands into a supergiant, bloating outwards as its internal structure changes, losing stability as it nears its final stages. In this swollen state, its outer atmosphere could have overflowed its Roche lobe, the region of gravitational dominance, and begun spilling material onto Zeta. This process is known as Roche lobe overflow, and it marks the beginning of mass transfer, one of the most complex and transformative phases in binary evolution. Zeta, the initially smaller star, would have begun accreting matter from its partner's envelope. This mass transfer wasn't always smooth. It likely occurred in violent bursts, with gas spiraling from one star to the other through a thin accretion stream or disk. The gravitational potential energy of this infalling material would have been converted into heat and radiation, possibly generating localized X-rays or changes in the stellar wind. Over time, this process could dramatically increase Zeta's mass, driving it into the O-type category, where it shines tens of thousands of times more brightly than the Sun. But the transformation wasn't purely physical. The gravitational bond between the two stars would have tightened or shifted, depending on how mass was exchanged. If the mass transfer was conservative, meaning no material was lost to space, the orbital separation might have decreased, bringing the stars into an even more intimate orbit. Alternatively, if the mass transfer was non-conservative, with matter flung into space by centrifugal force or radiation pressure, the orbit could have widened unpredictably. These dynamics created a gravitationally unstable environment, one that would eventually become vulnerable to disruption. As mass moved from the primary to Zeta, something paradoxical occurred. The donor star grew lighter, and Zeta grew more massive. In doing so, Zeta became the dominant member of the pair, but also inherited a destiny shaped by this imbalance. The more mass it gained, the more rapidly it burned through its hydrogen, and the more intense its stellar wind became. Yet, despite this growing dominance, Zeta remained tethered to the life and death of its companion. Their fates were still intertwined. During this time, the two stars would have emitted powerful stellar winds, streams of high-energy particles racing away from their surfaces. These winds interacted with each other in a region known as the wind collision zone. Here, supersonic flows of plasma crashed together, generating X-rays, shock fronts, and possibly magnetic reconnection events. Observatories today often look for such signatures in known massive binaries, as they offer insights into how high-energy astrophysics plays out on a stellar scale. Despite the violence of the energy exchanges, there was also an elegant synchrony to their motions. Like dancers in a tightly choreographed routine, the two stars orbited a common center of mass, each pulling the other across the fabric of space. Zeta would have watched, in a sense, as its partner grew brighter, hotter, then redder and more unstable. These final years before the supernova were a cosmic countdown, with all the signs written in light curves, mass loss rates, and atmospheric instability. There's another fascinating possibility during this stage: tidal locking. If the orbit was close enough, the two stars might have rotated in sync with their revolution around each other, always showing the same face. This would have created hemispherical differences in heating, mass loss, and wind generation, subtle effects, but ones that might have had cascading impacts on the system's evolution. In such tight systems, tidal forces can also induce mixing within the stars, stirring elements from the core to the surface, altering the path of nuclear fusion, and further complicating the evolutionary timeline. All of this, the mass transfer, tidal effects, wind interactions, unfolded over a short cosmic timescale. These massive stars burned through their fuel quickly, their lives compressed into millions of years. And then, finally, the moment came when the primary star reached the end of its road. Having exhausted its nuclear fuel, its iron core collapsed, and in an instant, the delicate balance of the binary was destroyed. The explosion of the companion, the supernova that would become Zeta's exile, was not merely a death. It was a rupture in the very framework of gravitational continuity the two stars had shared. In that moment, Zeta became unbound, flung outward by a combination of the sudden mass loss from the explosion and the inherited orbital velocity it once used to circle its partner. The tight orbit that had bound them now became a launching platform, sending Zeta on a new trajectory through the galaxy. But even now, Zeta Ophiuchi carries within it the chemical and dynamical fingerprints of that binary life. Its high rotational speed, likely increased by accreted angular momentum, its current mass, inflated beyond what a solitary star would have achieved in the same environment, and its singular motion through space, all are testaments to that earlier, more complex chapter. It is a lonely star today, yes, but it is not a self-made one. Zeta is a product of shared evolution, a legacy of an intimate and violent relationship. It once circled a Titan, exchanged energy and mass, and stood at the edge of a stellar cataclysm. That experience shaped not just its path but its very identity. And though its partner is gone, collapsed or destroyed, silent in the night, Zeta still speaks of that time in every spectrum, every shockwave, and every kilometer it travels across the galaxy. The moment of the supernova was both an ending and a beginning. It marked the death of Zeta Ophiuchi's binary partner and the simultaneous birth of Zeta's journey as a runaway star. But to understand how this single explosive event could so violently and effectively hurl Zeta across the galaxy, we must dive into the remarkable physics of supernova ejection mechanics, a dance of forces, momentum, and mass loss so extreme that it reshaped Zeta's fate in an instant. When a massive star, like Zeta's companion, runs out of fuel, it can no longer produce the outward pressure needed to counteract the crushing force of gravity. This triggers a core collapse supernova, one of the most violent events in the universe. In mere seconds, the star's iron core collapses into a dense neutron star, or possibly a black hole, while its outer layers are blasted outward at thousands of kilometers per second. This blast releases more energy in a moment than the Sun will emit over its entire 10 billion year lifespan. But in a binary system like the one Zeta belonged to, that explosion doesn't just destroy the star, it destabilizes the entire system. Binary stars are gravitationally bound, their mutual pull keeping them in orbit around each other. That orbit depends delicately on their combined mass. When the more massive companion explodes and suddenly ejects a significant portion of its mass, sometimes more than half of the entire system's total, it throws the balance into chaos. Let's visualize this. Before the explosion, Zeta and its companion orbited a common center of mass. Each had kinetic energy from its motion and potential energy from their gravitational attraction. When the companion explodes, this balance is shattered by two simultaneous forces: mass loss and asymmetric force from the blast. First, the sudden drop in gravitational binding due to mass loss weakens the gravitational glue that held Zeta in orbit. Second, if the explosion is even slightly asymmetric, the companion's core, now a neutron star or black hole, can recoil in one direction, and by conservation of momentum, Zeta can be propelled in the opposite direction, like a slingshot losing its anchor. This is where Zeta's story turns into a cosmic escape. With the companion's grip broken, and the leftover energy from its former orbital velocity preserved, Zeta becomes unbound, an object in ballistic motion, moving at tens of kilometers per second. The escape velocity from a typical binary orbit depends on the orbital separation and the masses of the stars. In a system like Zeta's, with close orbits and massive stars, this escape velocity can be quite high. Zeta retained its orbital momentum but no longer had anything to orbit. Now it was simply coasting forward at speed, like a spacecraft jettisoned from a launch vehicle. Astronomers have modeled this process in great detail, using simulations of binary systems undergoing core collapse. These simulations show that, depending on the timing, geometry, and asymmetry of the explosion, the remaining star can achieve velocities between 10 and 100 km per second, or even higher in rare cases. Zeta's current speed of around 24 km per second fits comfortably within this range, suggesting a typical but efficient ejection from a tight, close binary. One crucial component of this dynamic is that Zeta didn't have to be physically touched by the explosion. The supernova shockwave, while capable of moving through space at tremendous speed, wasn't what pushed Zeta out. Instead, the star's motion is largely due to the mechanics of mass loss and orbital dynamics. The explosion acted like a trigger, removing enough mass quickly enough to cancel the orbit and allow Zeta's velocity to carry it away. In other words, Zeta fled not because it was pushed, but because it was released. That said, the explosion may have had other lingering effects on Zeta. Depending on how close the stars were when the supernova occurred, Zeta may have been bathed in radiation and hit by shockwaves, which could have stripped some of its outer layers or altered its stellar wind. However, given that Zeta remains a massive O-type star today, the damage, if any, did not significantly reduce its mass or luminosity. It survived not just the disruption but the very environment of the explosion, a remarkable testament to its resilience. There's also the issue of directionality. Today, Zeta is speeding through space in a very specific trajectory. By tracking this path backward, astronomers have pinpointed the likely region of the supernova, the Upper Scorpius-Ob Association, where many massive stars have lived and died over the last 10 million years. This retrograde tracking not only supports the supernova ejection scenario, but also helps constrain the timing of the event. It likely occurred around 1 to 2 million years ago, and Zeta has been traveling ever since, an uninterrupted journey across the galaxy, imprinted with that moment of loss and acceleration. The dynamics of supernova ejection also offer insight into the companion's fate. If the explosion was asymmetric enough to hurl Zeta outward, then the collapsing remnant, whether a neutron star or black hole, must have experienced a recoil kick in the opposite direction. This supernova kick could have flung the remnant out of the system entirely, setting it on its own solitary path through space. In some cases, these remnants have been detected as high-velocity pulsars, zipping through the galaxy. If Zeta's companion became such a remnant, it may now be light-years away, drifting silently through the galactic halo, a ghost of the past that severed Zeta's tether. Finally, it's worth noting that while the scenario outlined here is the most probable, the precise mechanics of Zeta's ejection remain an active area of research. Every new dataset, from Gaia's improved astrometry to high-resolution X-ray and infrared observations, adds to the picture. With each refinement, astronomers are drawing a sharper outline of that moment 1 to 2 million years ago when a binary star system ended, and a new journey began. The incredible precision of modern astrophysical modeling allows scientists to simulate thousands of binary interactions and explosion scenarios, each with variations in mass, timing, and separation, to see which best fits Zeta's observed properties today. What we know with confidence is this: Zeta Ophiuchi was catapulted into space by the death of its companion. The mechanics of supernova ejection are elegant and violent all at once, transforming a gravitational bond into momentum, structure into chaos, and a stable system into a lone traveler. Zeta did not choose to run. It was flung, unmoored in an instant by the detonation of a star it once orbited. And now, millions of years later, it still carries that momentum forward, a silent, glowing remnant of that final burst of energy, still racing across the sky. Zeta Ophiuchi's journey is nothing short of miraculous. In a universe where massive stars are born to die in violence, where their very nature dictates short, furious lives, Zeta stands out not merely because of its luminosity or speed, but because it is a survivor. It endured the death of its binary partner, an event so destructive it could have easily destroyed or crippled it. And yet, here it is, still burning, still racing through space, still bearing the echoes of a cataclysm that would have unmade lesser objects. This resilience makes Zeta Ophiuchi an astronomical rarity, a living remnant of a destroyed system, a survivor of stellar death. In astrophysics, we often study the aftermath of supernovae by examining their remains, neutron stars, pulsars, black holes, and supernova remnants like the Crab Nebula. But Zeta Ophiuchi offers something different. It is not the corpse of a dead star, nor a fragment scattered by an explosion. It is the companion that got away, the star that withstood the breakup, maintained its structural integrity, and emerged from the ashes of its partner to tell the tale. To fully appreciate how rare and remarkable this is, consider what typically happens in close binary systems involving massive stars. When one of the stars explodes in a supernova, several things can occur. The system can become completely unbound, with both stars flung into space, often at high speeds. In some cases, the gravitational shock is so extreme that both stars are destabilized or even partially destroyed. In others, the companion gets pulled into the collapsing remnant, triggering a second explosion or forming an accretion-fed black hole. Very few companions survive intact. Those that do are often left changed, stripped, scarred, chemically enriched, or destabilized. Zeta Ophiuchi, though clearly transformed, remains whole. Its photosphere is intact. Its internal fusion processes continue undisturbed. It retains a stellar wind powerful enough to carve bow shocks through space. There are no visible signs of structural trauma, no evidence of mass loss sufficient to compromise its stellar classification. In a sense, it has not only survived the explosion, it has thrived in its aftermath. This survival implies several things about the conditions of the supernova and the nature of the binary system. First, the two stars must have been close, but not too close. Had Zeta been tightly bound within the expanding envelope of the primary during its red supergiant phase, it might have been swallowed or disrupted entirely. But their separation was just wide enough for Zeta to escape direct impact, while still close enough to gain substantial mass during the pre-supernova transfer phase. Second, the explosion itself, while powerful, must have been directionally favorable. Supernovae are not always symmetrical. Asymmetric core collapses can create kicks, launching compact remnants in one direction while simultaneously boosting the companion in the opposite. Zeta may have benefited from this cosmic slingshot, gaining not just release from the gravitational bond, but additional velocity from the directional energy of the explosion itself. It is quite possible that, had the explosion been even slightly more chaotic, Zeta would not have made it out intact. But survival is not just about structure. Zeta Ophiuchi also carries the narrative memory of its partner's death. Its motion through the galaxy, its bow shock, its high rotation rate, and possibly its internal chemical composition all bear the fingerprints of its earlier life in a binary system. Its present luminosity and mass are likely not what they would have been had it formed alone. The mass it gained from its companion, through Roche lobe overflow or wind accretion, may have increased its evolutionary clock, pushing it toward a faster burning, more energetic phase. In this sense, Zeta is not just a survivor, it is an evolved survivor, forever altered by its close brush with death. This makes Zeta Ophiuchi an invaluable subject of study for astrophysicists. It provides a living laboratory for understanding binary evolution, mass transfer dynamics, and post-supernova orbital mechanics. Its bow shock offers a real-world example of supersonic stellar motion and interstellar medium interaction. Its high-velocity trajectory helps refine models of supernova explosions and runaway star ejection. And its current state, massive, bright, and fast, offers clues about how surviving companions age, rotate, and lose mass after the breakup of a binary system. In many ways, Zeta represents the road not taken by its companion. The star that once orbited beside it ended in darkness, either collapsed into a dense remnant or completely destroyed. Zeta, however, was given a second act. It was not drawn into the death spiral. It did not collapse or fragment. Instead, it was cast outward, exiled but still radiant. And in this light, its role becomes symbolic. Zeta is not just a physical object moving through space, it is a witness, a messenger, and a reminder. It carries information not only about its own structure and motion, but about the conditions of its origin. It represents a survival pathway in a universe dominated by destruction. And while its journey may seem lonely, it is anything but meaningless. Every kilometer it travels is a silent record of the explosion that propelled it. Every shockwave it generates through the interstellar medium is a ripple of history, still moving outward through space and time. As we observe Zeta today, cutting through space with unyielding velocity, dragging its bow shock like a sail against the interstellar wind, we are watching a star in post-trauma motion. But it is not diminished. If anything, it is amplified by its ordeal. It is a survivor not just in the biological sense, but in the cosmic sense. It endured the worst the universe had to offer and emerged incandescent. Few stars can claim such a story. Even fewer live long enough to be seen telling it. Zeta Ophiuchi may have lost its partner, but in doing so, it gained something else: freedom, trajectory, and a story that spans across millions of years and hundreds of light years. In its light, we find both a beginning and an end. And in its motion, we find the echo of survival, not fragile, but fierce. Zeta Ophiuchi is not merely drifting through space, it is speeding through the galaxy, a stellar projectile hurled from its origin by a cataclysmic event. At a blistering pace of about 24 kilometers per second, or over 86,000 kilometers per hour, it slices through the Milky Way like a needle through silk. To the untrained eye, this might not seem particularly fast. After all, it takes light over 4 years to reach us from the nearest star. But in galactic terms, Zeta Ophiuchi is on a supersonic odyssey, capable of traveling thousands of light years over its stellar lifetime. Let's put this into perspective. At its current velocity, Zeta Ophiuchi could cover the average Earth-to-Moon distance in about 5 hours. In just 1 year, it travels over 750 million kilometers, a distance greater than 5 times the orbit of Earth around the Sun. Over the course of 1 million years, it will have moved over 24 trillion kilometers, or more than 2,500 light years. Considering that it likely has another few million years before it reaches the end of its own life and undergoes a supernova of its own, Zeta could easily cross an enormous portion of the Milky Way's disk, possibly reaching entirely different spiral arms from the one in which it was born. This kind of high-speed journey isn't unique to Zeta, but it is certainly exceptional. Runaway stars, those ejected from their birthplaces by violent processes like supernovae or gravitational interactions, form a distinct population. They are stars untethered from the clusters where they formed, often sent flying across the galaxy like shrapnel from an explosion. Some, like Zeta, are expelled by the sudden loss of mass and gravitational equilibrium in a binary system. Others are launched by three-body encounters, in which two stars orbiting each other interact with a third, and one is ejected with a massive boost in velocity. Whatever the mechanism, the result is the same: a stellar exile, flung far from its original home. Tracking the path of such stars is like conducting a forensic investigation across the galaxy. Using precise astrometric measurements, such as those provided by ESA's Gaia mission, astronomers can measure a runaway star's position, velocity, and trajectory with extraordinary accuracy. By projecting that path backward through time, they can often identify the region or cluster from which it originated. In Zeta Ophiuchi's case, its vector points back to the Upper Scorpius-Ob association, a nearby group of young, massive stars. This reinforces the idea that Zeta was born in a high-mass, high-energy environment where supernovae are relatively common. But Zeta's journey is far from random. The gravitational structure of the Milky Way ensures that even runaway stars follow curved paths, influenced by the galaxy's overall mass distribution. The disk, bulge, and dark matter halo all exert forces on Zeta's trajectory, gently bending it as it moves. This means that while it is no longer bound to a star cluster, it is still orbiting the galactic center, just on a more eccentric and solitary path. Unlike stars bound to clusters or star-forming regions, Zeta travels through a wide range of environments, crossing denser molecular clouds, low-density voids, and possibly even the halo regions above and below the galactic plane. Along the way, Zeta interacts with the interstellar medium, ISM, in profound ways. Its high velocity compresses the gas and dust in its path, creating a bow shock that radiates in infrared, shaping the environment like a ship plowing through water. It leaves a trail of turbulence in its wake, influencing local gas dynamics, potentially triggering or halting star formation in small, dense clouds it passes through. Though not as influential as supernova remnants, these high-speed stars are still agents of change, disturbing the medium through which they pass. Zeta's motion is not only dramatic but also diagnostic. Its speed, direction, and past trajectory provide astronomers with a living record of the supernova that launched it. The energy imparted to it during the explosion, and the direction in which it was hurled, encode information about the asymmetry and violence of the blast. If its companion remnant, perhaps a neutron star, can ever be located, the combined motions of both objects could yield a complete three-dimensional narrative of their shared history, a full arc from birth to destruction to exile. Runaway stars also challenge our understanding of galactic evolution. As these stars migrate far from their formation sites, they contribute to the chemical and kinetic mixing of the galactic disk. Zeta, for example, may carry heavy elements and isotopes enriched during its pre-ejection mass accretion phase. As it ages and ultimately ends its life in a supernova of its own, it will pollute a completely different part of the galaxy than where it was born, injecting energy and metals into a region that might otherwise have remained quiescent. In this way, runaway stars serve as mobile engines of enrichment, redistributing mass and momentum across the galaxy. Moreover, Zeta's journey underscores the fragility of stellar communities. Clusters of massive stars form together, evolve together, and often explode together, but they don't always stay together. Explosions, interactions, and chaotic motion break these stellar families apart. Over millions of years, the cluster dissolves, its former members scattered across the sky, each one carrying a piece of the original structure's legacy. Zeta is one such fragment, brilliant, fast, and alone. And perhaps most awe-inspiring of all is the fact that Zeta's story is still unfolding. Its motion through space is not yet complete, and its end has not yet come. It may travel for another 2 to 4 million years, eventually exhausting its nuclear fuel and collapsing into a neutron star or black hole, or exploding in its own supernova. If that happens, the echo of the original explosion that launched it will be mirrored, the cycle completing itself with a second cataclysm in a different corner of the galaxy. In this sense, Zeta Ophiuchi is not just speeding through space, it is writing its story across the stars, 1 kilometer per second at a time. Its velocity is not just a number. It is a legacy of violence, a measure of memory, and a prophecy of what is yet to come. And as it cuts its path through the dark, it reminds us that in the cosmos, nothing truly stands still, not even the stars. Before the blast that set Zeta Ophiuchi on its solitary journey through the galaxy, long before its bow shock ignited the interstellar gas in a luminous arc of motion, Zeta was not the dominant partner in its binary system. That role likely belonged to its now vanished companion, a more massive star whose death became Zeta's rebirth. But in the years leading up to the supernova, there was a silent exchange underway, a celestial transaction of matter and energy that would change Zeta Ophiuchi forever, the transfer of mass from one star to another. In high-mass binary systems like the one Zeta belonged to, this process is a fundamental driver of stellar evolution. It's not merely a one-way gift of gas, it's a profound reshaping of identity. The more massive star, evolving faster due to its higher core pressure and faster fusion rate, expands into a supergiant. As it does, its outer layers begin to overflow the gravitational boundary known as the Roche lobe, spilling matter onto its companion. For Zeta, this meant receiving not only mass but also angular momentum, energy, and even new elements synthesized in the donor star's interior. This process, known as Roche lobe overflow, often marks a turning point in the life of a binary system. It can happen gradually, or it can erupt in sudden bursts of instability. The companion star, in this case Zeta, begins to draw in material through an accretion stream, a funnel of gas that arcs from the donor's outer layers to the recipient's surface. If the stream is stable and dense enough, it may form an accretion disk, spiraling inwards before merging with the recipient star. The effect is dramatic. Zeta's mass increases, sometimes by several solar masses. This gain accelerates its nuclear fusion rate, boosts its luminosity, and can change the star's spectral classification entirely. This is likely what happened to Zeta Ophiuchi. It may not have always been an O-type star. It could have started its life as a B-type or even a lower mass star, massive, but not the dominant powerhouse we observe today. Through mass transfer, Zeta not only grew in mass, but also became rejuvenated, appearing younger and more energetic than it would have been had it evolved in isolation. This rejuvenation is a common consequence of binary interactions, often misleading astronomers into misjudging a star's true age based solely on its mass and temperature. But the impact of mass transfer doesn't stop at increased mass and brightness. The spin of the recipient star is often dramatically altered. As material spirals in from the donor, it carries angular momentum, spinning the recipient faster and faster. Zeta Ophiuchi likely experienced this too. It is now a rapid rotator, with equatorial velocities that may reach several hundred kilometers per second. This rapid spin influences everything from its internal convection to its magnetic field strength to the shape of its stellar wind. The star becomes oblate, slightly flattened at the poles due to centrifugal force, and its surface temperature can vary with latitude, hotter at the poles and cooler at the equator. Mass transfer may have also introduced chemical anomalies. As the donor star evolved, it fused heavier elements in its core: helium, carbon, nitrogen, oxygen. When it expanded and began shedding its outer layers, it may have transferred not just hydrogen-rich matter, but also fusion products, subtly altering Zeta's chemical composition. Spectral studies of Zeta Ophiuchi's surface may reveal enhanced nitrogen or helium lines, clues that suggest the star's outer layers are enriched by elements from a more evolved companion. This period of accretion may have lasted for thousands, or even hundreds of thousands of years. During this time, the system may have gone through cycles of stability and instability, as the donor lost mass and the balance of the binary shifted. As the mass ratio between the two stars changed, so did the dynamics of the orbit. Initially, the more massive companion would have orbited more slowly, pulling Zeta around a tight ellipse. But as Zeta grew in mass and the donor shrank, the center of gravity moved, the orbit widened or even destabilized, and the binary entered a precarious state, primed for separation the moment the supernova occurred. Importantly, Zeta's accretion phase also helped set the stage for its survival. The additional mass it received may have given it the structural integrity needed to resist the physical shock and radiation of the explosion. A less massive, more loosely bound star might have been disrupted or evaporated by the intense blast. But Zeta, now a bloated, fast-spinning, massive O-type star, had the inertia and energy to endure. It absorbed the sudden loss of gravitational binding, retained its velocity, and escaped. This transformation had long-lasting consequences. Zeta today is burning its nuclear fuel faster than it would have otherwise. It's shining brighter, evolving more rapidly, and is likely destined for a supernova of its own in a few million years. The mass it gained sealed its future, a future cut short by stellar standards, yet long enough for it to write its story across light years of empty space. What's more, this process wasn't visible at the time. Even with perfect instruments, we would have seen two bright stars orbiting each other, perhaps with subtle spectral shifts indicating gas movement. The real drama, the transfer of billions of tons of matter, the speeding up of a star's spin, the deep structural changes within its core, were happening beneath the surface. Invisible to the eye, yet monumental in consequence. In many ways, mass transfer is a quiet form of violence. It doesn't involve explosions or collisions, but it's just as transformative. It rewrites the destiny of both stars involved, often killing one faster, and propelling the other into a life it never would have had alone. For Zeta Ophiuchi, this meant exchanging a slow evolution for a high-speed journey, a solitary voyage defined not by where it was born, but by what it inherited. This invisible gift, the mass of a dying star, was both blessing and curse. It gave Zeta the power to survive, but also set it on a path of loneliness, speed, and inevitable collapse. In its current form, Zeta is both itself and the ghost of its partner, shaped by a hand that no longer exists. It is a hybrid entity, one whose present cannot be understood without reference to the past. And that past is written, in part, in the mass it carries, mass that once belonged to a companion now scattered among the stars. Zeta Ophiuchi's past may be defined by the loss of its companion and the sudden jolt into exile, but its future is equally dramatic, poised on the edge of stellar cataclysm. This is a star with immense power and limited time. The very features that make it fascinating, its mass, brightness, and speed, are also the reasons why it cannot last. Zeta is an O-type star, among the most massive and luminous stars in the universe, and with that distinction comes a sentence, a short, unstable, and violently terminal life. The laws of stellar physics are unyielding in this regard. Massive stars live fast and die young. While a star like our Sun can shine steadily for 10 billion years, Zeta Ophiuchi is expected to last only a few million. Its core burns with incredible ferocity, fusing hydrogen into helium at a pace that exhausts its fuel supply rapidly. This extreme rate of fusion is driven by its massive core pressure that requires tremendous heat, and thus rapid energy generation, to maintain equilibrium. At its core, Zeta Ophiuchi is in a state of dynamic balance. Gravity tries to collapse the star inward, while the outward pressure from radiation and thermal energy keeps it inflated. But this balance is not permanent. With every fusion reaction, hydrogen is depleted and helium accumulates in the core. Eventually, the core becomes saturated with helium, and hydrogen burning shifts to the shell surrounding the core. The core contracts and heats further, reaching temperatures high enough to begin helium fusion into carbon and oxygen. This process repeats as long as there's a viable fuel source, but each successive fusion stage is shorter and more unstable than the last. As Zeta enters these later stages of stellar life, it will begin to behave less like a steady beacon and more like a cosmic pressure cooker. The fusion of heavier elements, like carbon, neon, oxygen, and silicon, will proceed rapidly, each lasting only thousands or even hundreds of years. The final fusion product is iron, and iron represents a dead end in stellar physics. Fusion of iron absorbs energy rather than releasing it, leading to a catastrophic loss of outward pressure. In an instant, gravity wins. The core collapses. When this moment arrives, Zeta will become a supernova, a stellar explosion of unimaginable power. The collapse of the core into a neutron star or black hole will unleash an outward shockwave that rips the outer layers apart. The energy of this blast can briefly outshine an entire galaxy, hurling newly forged elements into space and leaving behind a remnant that could become one of the densest objects in the universe. This fate is practically guaranteed for a star of Zeta's mass. With more than 20 times the mass of the Sun, there is no path for it to fade gently into a white dwarf like low-mass stars do. It is doomed by its size, its brilliance a kind of terminal brightness, destined to explode in a final act of cosmic violence. The exact nature of this explosion, whether it produces a neutron star or collapses entirely into a black hole, depends on its final mass at the time of death. Zeta is currently losing mass through powerful stellar winds, a common feature of O-type stars. These winds strip away the star's outer layers over time, potentially removing several solar masses before the end. This loss could be amplified by pulsations, magnetic eruptions, or outbursts, especially as Zeta enters the later evolutionary stages like the Wolf-Rayet phase, a brief, transitional state characterized by even more extreme mass loss and naked helium-burning cores. If it ends its life with a mass above about 2.5 to 3 solar masses in the core, it will almost certainly collapse into a black hole. If slightly less, it may become a neutron star, a city-sized sphere of degenerate matter with a density so high that a teaspoon of its material would weigh billions of tons. Either way, the outcome will be dramatic, final, and invisible, unless the core becomes a pulsar, radiating beams of energy that sweep across the cosmos. But the implications of Zeta's future supernova go beyond its own demise. When it explodes, it will seed the galaxy with heavy elements, oxygen, silicon, iron, and more. These are the building blocks of rocky planets, of atmospheres, of life itself. The calcium in your bones, the iron in your blood, the oxygen you breathe, much of it was forged in the cores of stars like Zeta, and released in explosions like the one that awaits it. Zeta Ophiuchi is not just a dying star, it is a cosmic alchemist, preparing to transform its internal elements into the raw materials of future generations. Furthermore, the shockwave of its supernova will expand outward, heating and compressing interstellar gas. This can trigger new waves of star formation, creating entire stellar nurseries in the wake of destruction. This cyclical process, star birth, evolution, death, and rebirth, is the engine of galactic ecology, and Zeta Ophiuchi is part of it. Even in death, it will contribute to the vitality of the Milky Way, catalyzing change far beyond its immediate location. There's also the question of whether we'll see it happen. Zeta is about 366 light-years from Earth, close by cosmic standards. If it goes supernova in the next few million years, it will appear as a brilliant point in our night sky, possibly visible during the day. We, with our telescopes and satellites, will see them as data-rich phenomena, offering insight into the physics of core collapse, neutrino bursts, and element synthesis. Zeta's explosion could become one of the most studied events in human history, an opportunity to observe a nearby supernova in real time. Yet until that moment comes, Zeta remains in motion, still burning, still moving, still changing. It is unstable not because it is failing, but because it is living at full throttle. Its current state is a high-speed march toward entropy, a brilliant countdown clock ticking through the final stages of a stellar lifespan. It is luminous, yes, but also volatile, turbulent, and on edge. Each moment we observe it is another moment closer to the grand finale. And so, Zeta Ophiuchi's future is a paradox, both known and unknown, predictable and mysterious. We know its end will be explosive, but we do not yet know when. We know its life will be short, but we cannot yet see its final flare. What we do know is that it continues to be one of the most instructive, awe-inspiring, and tragic figures in the galactic storybook, a star caught between past and future, memory and prophecy, speed and stillness. The ultimate fate of Zeta Ophiuchi is written in its core, an inevitable collapse, a spectacular rebirth, a continuation of the very cycle that began with the explosion of its long-lost companion. In several million years, perhaps less, perhaps slightly more, Zeta Ophiuchi is expected to meet its end not with a whimper, but in a cosmic eruption of extraordinary power, a supernova of its own. And when that moment comes, the galaxy will tremble once more, echoing the violence that once flung it across the stars. This future supernova is not speculative fantasy, it's a predictable certainty for a star of Zeta's mass and spectral type. Stars like this, O-type giants burning at tens of thousands of degrees, radiating thousands of times more light than the Sun, simply cannot maintain their structure for long. They burn bright, live fast, and die young. Zeta Ophiuchi has already consumed much of the hydrogen in its core. Soon, on the cosmic timescale, at least, it will fuse helium, then carbon, and then progressively heavier elements in shorter and more unstable bursts. With each step toward iron, the star draws closer to collapse. Iron is the end of the line for fusion. Fusing iron consumes energy rather than releasing it, and once the star reaches this point, it can no longer support its own mass. Gravity wins. The core, now unable to resist the pressure bearing down on it, collapses in on itself in a matter of seconds. In that moment, Zeta Ophiuchi will undergo the ultimate transformation, from a massive, radiant being to either a neutron star or a black hole, depending on how much mass it retains in its final stages. The explosion that follows, the core collapse supernova, will be among the most energetic events in the universe. The outer layers of Zeta Ophiuchi, once held up by the pressure of fusion, will rebound outward with tremendous force as the core caves in. The resulting shockwave will blast through the star's surface at tens of thousands of kilometers per second, unleashing a radiant burst that could briefly outshine an entire galaxy. For a few short weeks, Zeta will become one of the brightest objects in the night sky, visible even in daylight, casting shadows at night, a new, guest star, just as ancient astronomers once recorded in 1054 AD when the Crab Nebula was born. If Zeta were to explode today, it would be a spectacle for Earth's astronomers, despite its distance of around 366 light-years. This is close, but not dangerously so. The radiation from the supernova, visible light, X-rays, gamma rays, neutrinos, would be intense, but not fatal for life on Earth. However, it would be the most significant stellar explosion observed in modern times, a rare chance to watch the full life cycle of a massive star culminate in its final act. Telescopes from around the world, and in orbit, would be turned toward the event, capturing every detail of the explosion and its aftermath. And the aftermath would be just as important as the event itself. As the stellar debris expands, it will enrich the surrounding space with newly forged elements: oxygen, neon, magnesium, silicon, sulfur, calcium, and iron, all created in the moments before and during the collapse. These elements will mix into the interstellar medium, becoming the building blocks for new stars, new planets, and eventually, perhaps, life itself. Every breath of air you take contains oxygen atoms born in supernovae like Zeta's future one. Every speck of iron in your blood was forged in such a cataclysm. In exploding, Zeta would become a cosmic seed, dispersing matter that will help build the next generation of stars. But the implications stretch even further. Depending on the density and structure of the surrounding interstellar medium at the time of explosion, the supernova remnant may take on elaborate shapes: rings, filaments, and arcs of glowing gas, pushed outward by the expanding blast wave. This remnant could persist for tens of thousands of years, slowly fading while astronomers study its composition and behavior. It may become a nebula, like the Veil Nebula or the Crab Nebula, visible through telescopes long after the star that created it has vanished. And what of the core? After the outer layers are ejected, the core itself will be compressed into something far denser than ordinary matter. If Zeta retains enough mass in its center, the collapse may result in a black hole, a point of infinite density from which not even light can escape. If slightly less massive, the result may be a neutron star, an object no larger than a city, yet containing more mass than the Sun, spinning rapidly and emitting beams of radio waves. It might become a pulsar, sweeping across space like a lighthouse and sending out pulses detectable here on Earth. This endpoint, supernova, neutron star, black hole, is a profound transformation, but it's also part of a grand cycle. Zeta's explosion would mirror the one that created it, the supernova that destroyed its companion millions of years ago. In a way, the two stars are locked in a poetic symmetry. One exploded and gave Zeta motion, mass, and a new destiny. Now Zeta, in time, will do the same, explode, move matter, and alter the fate of stars and gas far beyond its current location. It's a cosmic echo, a call and response across millions of years and thousands of light-years of distance. That legacy also includes the effects Zeta's explosion will have on neighboring space. Though not in a dense star-forming region now, by the time it explodes, Zeta may be closer to or embedded within a molecular cloud or gas-dense environment. The radiation and shockwave could compress this gas, kickstarting new waves of star formation. It's possible that entire stellar nurseries could be born from the pressure of Zeta's final breath, new stars lighting up in the nebula it leaves behind. This is how the galaxy renews itself. Massive stars like Zeta burn hard and fast, not only shaping their immediate surroundings while alive, but reshaping the galaxy through their deaths. They are both destroyers and creators. Their short lives sow the seeds for longer, more stable systems. And they remind us that the end of one star is not an ending at all, but a transition, a handing off of energy, momentum, and matter into the fabric of the cosmos. And so Zeta Ophiuchi, the runaway star that once fled the explosion of its companion, will become the explosion. The circle will close. The sky will change again. And long after its light fades, its influence will ripple through space, etched in gas clouds, newborn stars, and drifting atoms that once belonged to a star flung across the stars. The brilliant, glowing arc ahead of Zeta Ophiuchi is more than just a beautiful feature. It's a cosmic laboratory, a live demonstration of physics on scales and in conditions that are impossible to reproduce on Earth. Known as a bow shock, this structure forms as the star plows supersonically through the interstellar medium, compressing and heating the gas and dust in its path. To the eye, it might resemble the wake of a speedboat, but in truth, it is a dynamic, turbulent interface between stellar winds and the ambient medium, and it holds immense scientific value for understanding the physics of shockwaves across the universe. Zeta Ophiuchi's bow shock is particularly well-defined and striking. As it moves at approximately 24 km per second, it emits a powerful stellar wind, a high-velocity stream of charged particles flying outward from the star's surface at hundreds to thousands of kilometers per second. When this wind collides with the interstellar gas and dust, it doesn't blend gently, it slams into it like a wall, generating an intense shock front. The result is a curved, compressed shell of glowing material, shaped like a crescent or arc in the direction of the star's motion. This bow shock is more than a visual spectacle. It's a physical regime where extreme conditions play out in slow motion, observable from afar with telescopes across the electromagnetic spectrum. The density, temperature, and ionization state of the gas change drastically across the shock boundary, allowing astronomers to study how matter behaves when subjected to violent compression and heating. Unlike explosions that last moments, bow shocks are persistent. Zeta's has likely existed for tens of thousands of years, gradually evolving as it carves its way through space. One key concept at play here is the Mach number, a measure of speed relative to the local speed of sound. Zeta Ophiuchi is moving faster than the sound waves can travel through the interstellar medium, making it a supersonic object. This is what creates the shock. Much like a jet breaking the sound barrier on Earth creates a sonic boom, Zeta creates a permanent and continuous compression front in space. But unlike the brief sonic boom of a plane, the star's bow shock is a continuous, layered structure, containing both forward and reverse shocks. The forward shock is where the interstellar material is abruptly compressed and heated as it meets the stellar wind. Just inside of that lies the reverse shock, where the stellar wind itself is decelerated and compressed. Between these two is a turbulent, mixed region called the contact discontinuity, where instabilities can form, swirls, eddies, and small-scale shocks that propagate and evolve over time. This region is ripe with complexity, and studying it helps astronomers understand phenomena such as plasma turbulence, magnetic field amplification, and particle acceleration. In fact, these environments may also serve as natural particle accelerators, where electrons and protons are pushed to nearly relativistic speeds. This is crucial for understanding not only stellar dynamics but also the origins of cosmic rays, high-energy particles that permeate the galaxy. Zeta Ophiuchi's bow shock could be a low-energy analog of the environments found around supernova remnants, offering clues into how shocks of all sizes might contribute to the galactic cosmic ray population. To study these shocks, astronomers rely on multi-wavelength observations. In infrared, we see the dust heated by the shock front glowing with thermal radiation. In X-rays, we can detect the hot plasma generated by the high-speed collisions. In radio wavelengths, we can trace synchrotron emission from particles spiraling along magnetic fields, revealing the structure and strength of those fields. And in ultraviolet, we observe high-energy transitions from ionized atoms, providing temperature diagnostics for the shocked gas. All of these windows combine to provide a layered picture of shock physics, something that can't be achieved in any laboratory on Earth. The detailed structure of the bow shock is influenced by both internal factors, like the strength and composition of Zeta's stellar wind, and external factors, such as the density, temperature, and composition of the interstellar medium it travels through. If Zeta passes through a denser gas cloud, the bow shock compresses tighter and glows more brightly. If it enters a more diffuse region, the arc relaxes, becoming more extended and faint. This sensitivity makes bow shocks excellent probes of the local environment, allowing scientists to map interstellar density variations on parsec scales. Furthermore, the presence of dust grains in the shocked region introduces another layer of complexity. These grains can absorb energy, re-emit it at longer wavelengths, or even be destroyed by sputtering in the shock. Observing how dust behaves in these regions helps scientists understand dust evolution in galaxies, including how grains survive, grow, or erode under different conditions. Since dust is essential to the formation of planets and molecular clouds, its behavior in bow shocks has implications that extend all the way to planetary system formation. One fascinating aspect of bow shocks is their morphological diversity. While Zeta's is relatively symmetrical and well-defined, other stars show asymmetrical or distorted arcs, likely due to non-uniform motion, asymmetric stellar winds, or magnetic field influences. By comparing bow shocks across different runaway stars, astronomers can tease apart which properties are intrinsic to the star and which are shaped by its galactic journey. Zeta Ophiuchi, with its luminous arc, rapid motion, and powerful wind, provides a template for understanding how these phenomena play out. In fact, it's become one of the most studied examples of a stellar bow shock in astrophysics. Simulations and 3D models based on Zeta's parameters are used to validate theoretical predictions about shock structure, turbulence growth, and energy dissipation. These models, in turn, are applied to interpret more complex shock environments like those around supernova remnants, young stellar objects, and galactic jets. Shock physics is a cross-disciplinary field, linking fluid dynamics, plasma physics, magnetohydrodynamics, and high-energy astrophysics. Zeta's bow shock stands at the center of this intersection, offering both simplicity and complexity in its structure. It gives researchers a chance to observe nonlinear physical processes over immense scales, with effects playing out over thousands of years and trillions of kilometers. Ultimately, Zeta Ophiuchi's bow shock is not just a product of motion, it is a conversation between star and space, a visible record of interaction, energy exchange, and transformation. It teaches us that even in the vast silence of interstellar space, stars leave a trail of dialogue behind them. That dialogue is written in heat, light, compression, and turbulence, and it is one we are only just beginning to fully decode. Zeta Ophiuchi, with its immense mass and relentless speed, doesn't just leave behind a physical wake in the form of its bow shock, it also leaves behind a flood of high-energy radiation, invisible to human eyes but critical to astronomers trying to understand the most violent and energetic processes in the universe. This radiation, primarily in the form of X-rays and ultraviolet, UV, light, is a signature of its intense stellar winds, turbulent interactions with the surrounding medium, and complex surface dynamics. In many ways, Zeta is like a cosmic lighthouse, not just emitting visible light, but streaming powerful beams of high-energy photons across the galaxy, revealing its internal workings and its interactions with its environment. The star's X-ray emissions are particularly noteworthy because they offer a direct look into some of the most extreme processes occurring within and around Zeta Ophiuchi. High-energy X-rays are typically produced in regions where shock heating takes place, where matter slams into other matter at tremendous speeds, heating it to millions of degrees. In Zeta's case, this happens in several locations, within its stellar wind, in its outer atmosphere, and at the bow shock where the wind crashes into interstellar material. Zeta's wind is no gentle breeze, it's a furious stream of plasma, rushing outward at speeds of 1,500 to 2,500 kilometers per second. These winds aren't uniform, they're chaotic, clumpy, and variable. Within the wind itself, instabilities cause regions of gas to collide with each other, producing internal wind shocks. These are turbulent sites where gas is rapidly compressed and heated, reaching temperatures high enough to emit soft X-rays. Observing this emission helps scientists study the structure and variability of the wind, how it flows, how dense it is, and how it changes over time. Moreover, when Zeta's wind hits the surrounding interstellar gas and dust at supersonic speeds, it produces external shocks, another key source of X-ray radiation. These shocks compress and heat interstellar material to temperatures of several million degrees. While the bow shock is more dramatically visible in infrared due to heated dust, the hottest parts of the shock glow in X-rays. Observations with space telescopes like Chandra and XMM Newton allow astronomers to map these hot zones and measure their temperature, composition, and motion. This gives a real-time view of how stellar winds evolve as they crash through space. Zeta Ophiuchi also floods space with ultraviolet radiation, a hallmark of massive, hot O-type stars. This radiation originates from the star's intensely hot photosphere, where surface temperatures exceed 30,000 Kelvin, several times hotter than the Sun's. Such temperatures emit light predominantly in the ultraviolet part of the spectrum. In fact, Zeta's UV output is so powerful that it has significant consequences for its surroundings. First, this ultraviolet radiation ionizes the interstellar medium, stripping electrons from atoms and transforming otherwise neutral gas into a glowing plasma. This ionization front can extend far from the star, creating a bubble of high-energy plasma around it, further influenced by the motion of the star and the flow of its wind. Mapping this ionized region helps scientists understand the feedback that massive stars exert on their environment, how they shape, heat, and energize the very clouds that gave birth to them. Second, the UV light affects dust grains caught in the bow shock. Ultraviolet photons are energetic enough to erode and shatter dust particles, breaking chemical bonds and altering grain structures. This erosion process, called photoevaporation, plays a key role in dust survival in harsh environments. By analyzing changes in dust size, shape, and emission properties, scientists gain insight into the life cycle of cosmic dust, which is vital for forming new stars, planets, and even complex molecules. Third, the UV radiation provides a tool for studying stellar atmospheres and winds in high detail. Astronomers use UV spectroscopy to observe specific atomic and ionic lines, such as those from carbon, nitrogen, silicon, and iron, which reveal the star's composition, temperature gradients, and wind velocities. Shifts in these spectral lines can also signal changes in wind speed or the presence of magnetic activity, helping to build a complete picture of Zeta's outer layers. One of the most remarkable things about Zeta Ophiuchi's high-energy radiation is how much it tells us without needing to see the star directly in optical light. In fact, much of Zeta's X-ray and UV output penetrates dust and gas that would otherwise obscure our view. This allows scientists to peer into regions of the bow shock and the wind environment that are hidden in visible wavelengths. The use of multi-wavelength observation, blending data from infrared, visible, ultraviolet, and X-ray, creates a composite image of Zeta as a complex, multidimensional engine, driving physics in every direction. Another fascinating aspect is the potential presence of magnetic fields around Zeta Ophiuchi, hinted at through fluctuations in X-ray and UV emission. If confirmed, these fields could influence the wind's structure, create co-rotating interaction regions, SIRs, and channel energy into specific directions. Observing how these fields interact with the wind and bow shock could yield vital insights into stellar magnetohydrodynamics, a field still rich with unanswered questions. Finally, the high-energy radiation Zeta produces could one day signal its end. In the lead-up to a supernova, massive stars often undergo unstable stages marked by outbursts of radiation, shocks, and increasing variability in their winds. Monitoring Zeta's X-ray and UV output over long timescales could help scientists detect early warning signs, clues that its core is reaching the final stages of nuclear fusion. These could include sudden flares, irregular brightening, or changes in wind density and velocity. In this way, high-energy monitoring becomes a stellar early warning system, giving us a rare opportunity to watch a supernova precursor in action. Zeta Ophiuchi, therefore, is not just a visual phenomenon or a fast-moving celestial body. It's a high-energy powerhouse, illuminating its surroundings with radiation that tells a deeper story. It reveals the behavior of stellar winds, the structure of interstellar shocks, and the evolution of massive stars on the brink of collapse. With every X-ray photon and every burst of ultraviolet light, Zeta sends out a cosmic message, one that scientists are learning to read with ever-increasing clarity. Zeta Ophiuchi's life on the run is not aimless. It's a journey written in the fabric of spacetime, and one that scientists have meticulously traced across hundreds of light years. By mapping its motion with exquisite precision, astronomers have been able to reconstruct its past, deducing where it came from, when it was ejected, and even offering insights into what the environment was like when that dramatic ejection occurred. This is not just an exercise in stellar detective work. It's a way of rewinding cosmic history, using the laws of physics and data from modern observatories to follow a trail of motion stretching back millions of years. The process begins with careful observations of Zeta Ophiuchi's proper motion, its apparent movement across the sky relative to distant background stars. This motion, though incredibly slow by human standards, is measurable over time with high-resolution telescopes and long baseline data from missions like ESA's Hipparcos and the more recent Gaia Observatory. Gaia, in particular, has revolutionized this field by providing astrometric measurements with micro-arcsecond accuracy, allowing scientists to track the star's path with near-surgical precision. Alongside proper motion, astronomers also measure the star's radial velocity, its speed moving toward or away from us, using the Doppler shift in its spectral lines. Combining proper motion, radial velocity, and distance gives us the star's three-dimensional velocity vector, a complete map of how it's traveling through the galaxy. In the case of Zeta Ophiuchi, these measurements show that it is moving at an impressive 24 km per second, relative to the surrounding interstellar medium. But more importantly, this trajectory is not random. By projecting its current velocity backward through time, accounting for the rotation of the Milky Way and gravitational influences from the galactic potential, scientists can simulate where Zeta Ophiuchi has been. These simulations trace its path in reverse, like following skid marks back to the moment a vehicle swerved off the road. What they've found is astonishing. Zeta appears to have originated from the Scorpius-Centaurus-OB association, a region of space rich in young massive stars. More specifically, its path intersects with a subgroup known as Upper Scorpius, located approximately 400 to 500 light-years away. The timing of this intersection is just as telling. Zeta's backward trajectory intersects this region about 1 million years ago, the same timeframe during which other stellar members in the group exhibit signs of past supernova activity. This is compelling evidence that Zeta Ophiuchi was once a part of this cluster, and was violently ejected during a binary disruption caused by a supernova explosion. This kind of stellar ejection is a well-known mechanism, sometimes referred to as the Blau mechanism, after the astronomer Adrian Blau who first theorized it in the 1950s. In the Blau scenario, two massive stars orbit each other closely in a binary system. When one goes supernova, the sudden loss of mass and gravitational binding can slingshot the surviving star out of the system at incredible speeds. In Zeta's case, its motion is a smoking gun, and the precise alignment of its trajectory with Upper Scorpius provides direct observational confirmation of this theory. But the motion mapping doesn't stop at Zeta alone. Astronomers have also searched for neutron stars or pulsars that might be the leftover remnant of the star that exploded. If a compact object were found on a trajectory that converges with Zeta's path 1 million years ago, it would provide powerful evidence of a shared origin, a moment when both objects were catapulted in opposite directions, each carrying away momentum from the binary's disruption. So far, no definitive companion has been identified, but the search continues, particularly as new data from Gaia continues to refine the positions and motions of millions of stars in our galaxy. The mapping of Zeta's motion also intersects with another area of astrophysical research: runaway stars and galactic structure. By tracing the motions of stars like Zeta, astronomers can map the distribution of stellar clusters, spiral arm patterns, and the influence of galactic tides. These runaway stars act like test particles in a gravitational experiment, revealing the shape and strength of the Milky Way's potential field. In essence, Zeta becomes a tracer, not just of its own history, but of the dynamics of the galaxy itself. Even more intriguing is how Zeta's path might interact with interstellar matter. By tracking its journey, scientists can predict when and where the star has passed through denser or thinner regions of gas and dust. This helps explain variations in the shape and brightness of its bow shock and may correlate with regions of prior star formation or supernova remnants. In a way, Zeta is not just moving through space, it's sampling it, recording its density, texture, and turbulence with every kilometer traveled. Additionally, long-term monitoring of Zeta's motion provides a rare chance to observe how a high-mass star evolves outside of a cluster environment. Most O-type stars are found in dense associations or OB clusters, where their development is influenced by nearby stars and interactions. Zeta, having been ejected, is now evolving in relative isolation, and its path through the galaxy offers a chance to study how such a star behaves when removed from the usual cradle of stellar activity. This motion also has future implications. By projecting its path forward, astronomers can predict where Zeta will travel over the next few million years. It may eventually exit the local spiral arm, plunge into a new region of the galaxy, or intersect another area of dense molecular gas. These predictions help us understand the long-term impact of runaway stars on galactic evolution, as they carry energy, momentum, and heavy elements far from their birthplaces. In summary, mapping Zeta Ophiuchi's motion is not just a record of where it's been, it's a gateway to understanding stellar dynamics, binary evolution, galactic architecture, and supernova physics. Through a combination of astrometry, spectroscopy, and dynamical modeling, astronomers have traced its origin, revealed the likely cause of its ejection, and even hinted at the remnants it left behind. Every step of its million-year journey across space tells a story of force, loss, survival, and forward momentum, and with each new observation, that story becomes clearer, richer, and more profound. Zeta Ophiuchi's story, though remarkable, is not an isolated one. In fact, it is part of a larger and fascinating family of objects known as runaway stars, stellar fugitives that have been flung from their birthplaces at high velocities, often due to cataclysmic or gravitational events. While Zeta stands out because of its mass, bow shock, and well-documented path, it represents just one member in a cosmic population that stretches across the Milky Way and beyond. Runaway stars, in general, are vital agents of galactic evolution, dispersing energy, heavy elements, and turbulence across vast distances as they race through space. Astronomers have catalogued hundreds of confirmed and candidate runaway stars, many of which are O and B-type stars, the most massive and luminous stellar classes. These stars are known to form in dense stellar nurseries, often alongside dozens or even hundreds of others. In such crowded environments, the gravitational dance between stars can be chaotic, and occasionally it results in violent ejections. The two primary mechanisms that can launch stars into high-speed trajectories are dynamical interactions and binary supernova disruptions, both of which have left clear fingerprints in many of these celestial exiles. The dynamical ejection scenario typically occurs in young star clusters, where gravitational interactions between multiple stars or binary systems can fling one or more members outward. Imagine a cosmic billiard game, where stars act as massive balls moving through a crowded table. A close pass or a multi-body encounter can redistribute momentum dramatically. If two binaries interact, one component can be captured into a tighter system, while another is hurled out at escape velocity. These stars can be ejected at speeds of tens to hundreds of kilometers per second, depending on the mass and proximity of the interaction. The binary supernova scenario, as seen in Zeta Ophiuchi, involves the sudden death of one star in a binary pair. When a massive companion explodes, the gravitational bond is broken almost instantaneously. The surviving star, once locked in orbit, now flies away at the same speed it had in the binary system, often in excess of 30 to 40 kilometers per second. This mechanism produces stars that carry the hidden trauma of their partner's violent end and may sometimes be found moving in tandem with a compact remnant, such as a neutron star or pulsar. In some rare cases, these remnants are also runaway objects, moving away in the opposite direction. Runaway stars are classified by their space velocity, the combined speed derived from proper motion and radial velocity. A common threshold used to label a star as a runaway is 30 km per second or more relative to the average motion of its local stellar population. However, some stars far exceed this. The so-called hypervelocity stars, discovered more recently, move at hundreds or even thousands of kilometers per second, and are believed to be ejected by interactions with supermassive black holes at galactic centers. These extreme cases are rare, but they reveal the full spectrum of stellar motion possible in the universe. What makes runaway stars particularly interesting is their influence on galactic structure and evolution. Unlike typical stars that remain in clusters or spiral arms, runaway stars inject energy and radiation into new environments, sometimes triggering star formation in their path. As their winds and radiation collide with interstellar clouds, they compress gas, heating it and potentially causing localized gravitational collapse. In this way, runaway stars act as mobile agents of feedback, altering regions far from where they were born. Moreover, when runaway stars eventually reach the end of their lives, as Zeta Ophiuchi will, they go supernova far from their point of origin. This has two profound consequences. First, the exploded star enriches remote regions of the galaxy with heavy elements like iron, oxygen, and silicon, elements crucial for planet formation and life as we know it. Second, the supernova remnant itself can further trigger new star formation or drive shockwaves through previously undisturbed regions, reshaping the structure and chemistry of interstellar space. This dispersal of material contributes to the galactic recycling process, whereby matter is redistributed and reused across cosmic time. Runaway stars also serve as kinematic probes, revealing the gravitational and dynamic history of the Milky Way. By mapping their paths and velocities, astronomers can infer the mass distribution of the galaxy, the locations of past stellar clusters, and even detect perturbations caused by unseen objects, like dark matter clumps or black holes. The trajectory of a runaway star through the galactic disk, for example, may reveal wobbles or distortions that are not visible in starlight alone. Observationally, identifying a runaway star involves more than just speed. These stars often display peculiar velocities, meaning they deviate from the average motion of nearby stars. They are sometimes found in regions devoid of other young stars, which is unusual for massive O or B-type stars that typically form in clusters. They may also show chemical signatures of past interactions, such as enriched helium or nitrogen, suggesting past mass transfer events with a binary companion. In some cases, astronomers have even detected runaway binaries, where two stars are still gravitationally bound despite their high speed, having survived ejection as a system. Famous examples of runaway stars include A Aurigae and Mu Columbi, which appear to be moving in opposite directions from a common origin point in the Orion Nebula. Their paths converge with that of Iota Orionis, a tight binary system, suggesting a dramatic three-way interaction millions of years ago. This event is one of the most well-documented cases of dynamical ejection, providing a real-life example of how gravitational interactions can radically alter stellar trajectories. Another well-known case is the B X-ray binary LS5039, a high-mass X-ray binary system consisting of a massive O star and a compact companion, likely a neutron star. This system is also speeding away from a nearby cluster, suggesting it was ejected during a supernova event, similar to Zeta Ophiuchi. The presence of X-ray emissions confirms active accretion, making it a rare example of a runaway binary with ongoing energetic interactions. Runaway stars are also important in extragalactic astronomy. While more difficult to detect, these high-speed stars exist in other galaxies as well. Their presence helps us understand whether galactic dynamics, black hole interactions, and stellar evolution operate similarly beyond the Milky Way. The discovery of hypervelocity stars flying out of the galactic center has even led to the theory that binary interactions with Sagittarius A, our galaxy's central supermassive black hole, can eject stars at escape velocity. These hypervelocity stars are technically a subset of runaways, but they push the limits of what's physically possible in terms of speed and ejection mechanisms. In essence, Zeta Ophiuchi is a local representative of a widespread, highly influential class of stars. These stellar nomads tell stories of explosive ends, chaotic beginnings, and gravitational forces strong enough to reshape stellar destinies. They travel alone, but their stories are not isolated. Collectively, runaway stars are the fingerprints of galactic violence, the wandering witnesses of ancient catastrophes. They carry information across light years, evidence of where stars once lived, how they died, and what they left behind. In every runaway star, we find a thread of cosmic history unraveling across time and space. And as astronomers follow those threads through proper motion, radial velocity, bow shocks, and supernova remnants, they reconstruct not just the lives of individual stars, but the grand, interconnected story of the Milky Way itself. Zeta Ophiuchi's present isolation stands in stark contrast to the environment in which it was born. Today, it cuts a solitary path across the galaxy, a blazing outlier set against the dark sea of interstellar space. But once upon a time, millions of years ago, it was not alone. Zeta Ophiuchi likely began its life in the company of dozens, perhaps hundreds, of other stars, bound together in a stellar cluster formed from the same collapsing cloud of gas and dust. Understanding this cluster, now far behind in space and time, helps us reconstruct Zeta's origin story, offering critical context for the cataclysm that changed its fate. Massive stars like Zeta Ophiuchi almost never form in isolation. Their birth requires massive molecular clouds with the right density and temperature to allow gravitational collapse. These clouds typically fragment, forming clusters of stars rather than individual, isolated objects. The regions where these clusters form, often referred to as OB associations or stellar nurseries, are hotbeds of dynamic activity, where young stars shine intensely, interact gravitationally, and evolve rapidly. It is in one of these stellar cradles that Zeta Ophiuchi likely first ignited its nuclear core. Astronomers, through a combination of astrometric tracing and kinematic modeling, have long suspected that Zeta originated from the upper Scorpius subgroup of the Scorpius, Centaurus OB association. This region, located approximately 400 to 500 light-years from Earth, is known to be a rich and active stellar nursery, one of the nearest such regions to our solar system. The stars within it are young, hot, and often still surrounded by remnants of the gas clouds from which they were born. It's a place where massive stars like Zeta are born in close quarters, making binary systems and gravitational interactions common. Rewinding Zeta's path across space, using precise measurements of its motion, both tangential and radial, astronomers have aligned its trajectory with Upper Scorpius to about 1 to 2 million years ago. This corresponds with both the star's estimated age and the timing of potential supernova events in the region. The convergence of motion between Zeta and the Upper Scorpius subgroup isn't just a coincidence. It strongly supports the idea that Zeta was once nestled within a dense stellar cluster before it was violently cast out. These ejections are not uncommon in massive clusters. In fact, the intense gravitational interactions that occur among tightly packed young stars often lead to complex outcomes. Binary systems can merge, form triple systems, or even experience close encounters that eject one or more stars. Sometimes, these dynamics are enough to push a star out of the cluster. But more commonly, in Zeta's case, it's the binary supernova scenario, where one member of a massive binary explodes, that acts as the primary driver of such ejection. The cluster itself, having likely continued to evolve without Zeta, now sits far behind in its journey. The Scorpius, Centaurus association is loosely bound and is dispersing over time, with stars moving away from the core as they age. In a sense, the environment that gave birth to Zeta is slowly unraveling, while Zeta itself was launched out ahead of it at high velocity, leaving behind its siblings and the remnants of its early life. There's also the possibility that Zeta's birth environment was part of a subcluster within the broader OB association, a more compact group that has since dissolved or spread out. This is a common fate for young stellar clusters. Many are unbound from the start, and gradually disperse due to the loss of gas and the dynamical interactions among stars. If Zeta's cluster has since dissipated, tracking its remnants becomes more difficult, but not impossible. Astronomers can still identify co-moving stars, those with similar ages, compositions, and motions, that likely share a common origin with Zeta. One technique used in this process is chemical tagging. By analyzing the chemical fingerprint of Zeta Ophiuchi, its unique blend of elements and isotopes, astronomers can look for stars with nearly identical compositions. Stars formed from the same gas cloud generally share similar metallicity and abundance ratios, so finding a match can be a powerful clue. If a group of stars shares Zeta's motion and chemical makeup, they likely form together, even if they are now widely separated. Finding Zeta's lost cluster siblings can also illuminate the conditions of star formation in the region. For example, was the original cloud turbulent? Was it part of a triggered star formation event, perhaps caused by a prior supernova shockwave? These questions are essential to building a comprehensive picture of how stars like Zeta Ophiuchi are born, live, and in some cases, are cast out into the galaxy. Importantly, the connection to a cluster gives additional weight to the idea that Zeta was once part of a binary system, which is extremely common among massive stars. Observations suggest that 70% or more of O-type stars are born in binaries or higher-order multiples. Clusters provide the gravitationally rich environments necessary for forming and maintaining such systems during the early phases of stellar evolution. Once formed, these binaries may undergo complex interactions, including mass exchange, orbital tightening, and eventually, supernova-induced disruption, leading to cases like Zeta's. There is also a compelling observational benefit to confirming Zeta's cluster origin. It allows scientists to calibrate models of stellar motion and disruption. When astronomers simulate supernova ejections or gravitational interactions, they need real-world data to test their predictions. Zeta's path, paired with a clearly identified origin point, becomes a benchmark case, one of the few runaway stars with such a detailed and traceable history. Moreover, this knowledge feeds back into our understanding of stellar population dynamics. Clusters are not static, they evolve and decay, and their stars disperse over time. Runaway stars like Zeta, while dramatic, are just one manifestation of the dynamic nature of star groups. By tracing these stars and linking them to their origins, we gain insights into the lifespan and structure of stellar associations, the efficiency of star formation, and the long-term fate of the stars that emerge from them. Zeta Ophiuchi's past is thus not just a tale of escape, it is a chapter in the life of a cluster that once shimmered with youth and stellar birth. Now that cluster may be dimmer, quieter, and more spread out, but in Zeta's supersonic trajectory, it has left a legacy. A moving monument to its past. And even as Zeta races ever farther from that origin, the clues to its birthplace remain etched into its motion, its chemistry, and the very structure of its bow shock, a brilliant arc chasing a memory. Zeta Ophiuchi's bow shock is not a static structure frozen in space. It is a living, evolving phenomenon shaped by the ever-changing relationship between the star and its galactic environment. Like a boat forging through shifting tides, Zeta's path through the interstellar medium constantly exposes it to new conditions, each of which subtly or dramatically alters the form of the bow shock that surges ahead of it. Over time, this seemingly simple glowing arc becomes a dynamic laboratory, encoding not just the behavior of the star's wind but also the invisible texture of space itself. A bow shock forms when a star with a powerful stellar wind moves at supersonic speeds through the interstellar medium, ISM. The wind, a torrent of charged particles and radiation, plows into the surrounding gas and dust, compressing and heating it to the point where it glows, primarily in the infrared, but also potentially in radio, optical, and even X-rays in high-energy cases. The balance between the ram pressure of the stellar wind and the density of the ISM determines the location, shape, and brightness of the Ballistic's arc. However, the interstellar medium is not uniform. It is a patchwork of dense molecular clouds, tenuous ionized regions, clumpy neutral gas, and dust filaments, each with varying pressure, composition, and magnetic fields. As Zeta Ophiuchi plunges through these different regions, the properties of the ISM around it change, and so too does the bow shock that forms at the interface. Sometimes the arc may tighten or collapse inward as it enters a denser region. Other times, it may expand or weaken when it passes through more rarefied gas. This variation causes the bow shock to be in perpetual flux, its curvature, thickness, and intensity continuously responding to the interstellar terrain. The bow shock standoff distance, the space between the star and the apex of the shock, is a crucial variable in understanding this evolution. It is dictated by the equilibrium between the outward momentum of the stellar wind and the inward pressure of the interstellar material. If the interstellar density increases suddenly, the bow shock gets pushed closer to the star. If it decreases, the bow shock can relax and shift outward. Observations of changes in the standoff distance over time are therefore powerful tools for mapping variations in the ISM that would otherwise be invisible. Similarly, the wind strength of Zeta Ophiuchi is not necessarily constant. As the star evolves, the temperature, luminosity, and mass loss rate can fluctuate, sometimes significantly. For massive O-type stars like Zeta, stellar winds are driven by radiation pressure, and small changes in surface temperature or chemical opacity can cause large variations in wind output. If Zeta enters a more active evolutionary phase, its wind could intensify, pushing the bow shock outward. Conversely, a decrease in wind momentum could cause the shock to collapse slightly inward. Adding to this complexity are magnetic fields, both from the star and the interstellar medium. These fields can shape the direction and structure of the shocked gas, bending the bow shock's arc or introducing asymmetries in its brightness and thickness. In some cases, the bow shock may display ripples, or tails, signatures of instabilities forming at the boundary where the stellar wind and ISM meet. These features can evolve over time as the magnetic field configuration shifts or as turbulence in the ISM disturbs the flow. Another important dimension to bow shock evolution is motion through a density gradient. The Milky Way's disk contains spiral arms, regions of enhanced star formation and gas density separated by lower density interarm regions. As Zeta Ophiuchi travels through the galaxy, it may enter or exit these large-scale structures, resulting in long-term evolution of its bow shock over thousands or millions of years. For instance, if Zeta is now entering a more tenuous interarm region, we might expect to see the bow shock gradually fade or widen over time. Recent infrared observations, particularly from NASA's Spitzer Space Telescope and ESA's Herschel Space Observatory, have captured subtle asymmetries and time-variable features in bow shocks around massive stars. Although most observations of Zeta's bow shock are snapshots, future missions capable of monitoring the same object over decades could detect the slow evolution of the shock structure. This would allow astronomers to reconstruct a sort of time-lapse of how the shock morphs, effectively turning the bow shock into a real-time indicator of changing galactic conditions. Advanced 3D magnetohydrodynamic (MHD) simulations have been instrumental in helping astronomers understand this evolving behavior. These models take into account not just the movement of the star and its wind, but also the three-dimensional structure of the ISM, magnetic field lines, and even dust grain dynamics. By running simulations under different assumptions, varying the ISM density, wind strength, magnetic field direction, scientists can match theoretical outcomes to observed shapes of Zeta's bow shock and predict how it might evolve in the future. Interestingly, there's also evidence that feedback loops may influence the evolution of the shock. As the bow shock heats and compresses interstellar material, it may temporarily change the local conditions, affecting subsequent ISM behavior, including gas cooling, dust destruction, and even the triggering of star formation in nearby clumps. This kind of feedback means that Zeta's motion isn't just passive, it actively modifies its environment, which in turn reacts and reshapes the bow shock. Over long periods, This can result in nonlinear evolution, where small changes snowball into significant transformations of the bow structure. From an observational perspective, multi-wavelength data is essential to track these changes. Infrared reveals warm dust in the bow shock, while radio waves can show molecular gas compressed by the shock front. Ultraviolet and optical light can pick up emission lines from ionized gas, and X-rays may trace the hottest regions where the most intense compression occurs. Future telescopes like the James Webb Space Telescope and LUVOIR, if launched, may offer higher resolution, time-series imaging that can capture this evolution in unprecedented detail. Ultimately, Zeta Ophiuchi's bow shock acts like a cosmic weather vane, a responsive, shape-shifting structure that tells us not only about the star's intrinsic properties but also about the galactic winds and clouds it encounters on its journey. Over millennia, as Zeta traverses different environments, the shock will continue to evolve, possibly fading if the wind weakens, or brightening if the star charges into a denser cloud. In this way, the bow shock becomes not just a symbol of motion, but a record of interaction, a dynamic interface where stellar life meets the vast and volatile expanse of the Milky Way. Understanding the full complexity of Zeta Ophiuchi's journey through space, and the physical structures it creates along the way, requires more than observation. While telescopes provide snapshots and spectra that reveal real-time characteristics of the star and its bow shock, truly unraveling the intricate physics involved demands a powerful tool: 3D simulations. These computational models allow scientists to recreate the conditions surrounding Zeta Ophiuchi in 3 dimensions and evolve them over time, providing a window into both its past and future. With these simulations, researchers can experiment with parameters like wind strength, velocity, ambient gas density, and magnetic fields, and observe how the star's environment would respond across thousands or even millions of years. These models are far more than artistic renderings. They are based on the mathematics of hydrodynamics, magnetohydrodynamics, MHD, and radiative transfer. At the heart of a simulation lies the effort to numerically solve the equations that govern the behavior of fluids, specifically, how stellar winds and interstellar material move, collide, compress, and heat under the influence of gravity, pressure, magnetic fields, and radiation. For a star like Zeta Ophiuchi, with its powerful O-type stellar wind and supersonic speed, these interactions are anything but simple. The bow shock structure forms, evolves, fragments, and morphs based on the subtle interplay of these forces. Simulating this kind of environment in 3 dimensions is essential because real space is not flat or symmetrical. For instance, bow shocks are rarely perfect semicircular arcs. They may be distorted by inhomogeneities in the interstellar medium, or shaped by the star's own magnetic fields and rotation. 2D models might show general trends, like how a wind meets resistance from incoming gas, but only 3D models can capture the true complexity: turbulent eddies in the shock, off-center asymmetries, spiraling instabilities, and the curvature of motion through varying galactic gradients. One critical application of 3D modeling in Zeta Ophiuchi's case is testing how density variations in the interstellar medium affect the evolution of its bow shock. By simulating a region of space where Zeta is moving through a medium with fluctuating gas density, perhaps denser clouds followed by more rarefied zones, scientists can observe how the bow shock expands, contracts, and shifts in real time. These simulations have shown that a denser region compresses the bow shock tightly against the star, increases its temperature, and produces more intense emission in infrared and X-ray wavelengths. Conversely, a less dense region allows the shock to spread out and cool, possibly even diminishing in visibility. Another valuable insight gained from simulations comes from the interaction between stellar wind variability and shock structure. Although Zeta Ophiuchi currently has a powerful wind, stellar winds are known to fluctuate over time, either due to internal processes in the star or as part of its long-term evolution. By simulating scenarios in which the wind weakens or strengthens, researchers can observe corresponding changes in the bow shock's standoff distance and shape. These dynamic models can even predict delayed responses, where the shock takes time to reconfigure after a change in the star's output, akin to a ripple moving through the bow of a ship after the engine throttles back. Yet another layer of complexity comes from magnetic fields. both those carried by the stellar wind and those embedded in the interstellar medium. Magnetic fields can guide the flow of ionized gas and act as a confining force that resists compression. In a 3D MHD simulation, magnetic fields are visualized as curving lines of force that thread through space and can shape the bow shock in subtle ways. They may suppress certain instabilities that would otherwise form at the boundary between the stellar wind and the ISM, or they may amplify small perturbations that cause the shock to ripple or bend. In the case of Zeta, the bow shock appears relatively smooth and symmetric, but 3D models suggest this might change as the star moves into regions with more tangled or turbulent magnetic fields. Crucially, these simulations also help scientists test theories about runaway star dynamics themselves. Specifically, what happens when a star like Zeta is ejected from a binary system by a supernova. Researchers can simulate the orbital configuration of two massive stars in close proximity, track how one explodes, and observe the resulting gravitational slingshot that propels the surviving star. These simulations help fine-tune our understanding of the Bloom mechanism, showing how different orbital separations and supernova mass loss rates affect the ejection speed and trajectory. In some simulations, stars like Zeta can be ejected at speeds of 30, 40, or even 100 km per second, depending on the geometry of the system. Furthermore, modern simulations are increasingly capable of incorporating dust dynamics into the model, especially important for Zeta Ophiuchi, whose bow shock glows brightly in the infrared due to warm dust heated by stellar radiation. Dust grains behave differently than gas. They are more massive, more sluggish to react, and can be destroyed or eroded under high-energy conditions. Simulating dust behavior allows astronomers to reproduce the infrared observations of Zeta's bow shock with remarkable accuracy, and to estimate the types of dust present, their sizes, and how long they survive in the harsh environment created by Zeta's movement. Perhaps the most exciting frontier of 3D modeling lies in the realm of time-evolving simulations. With powerful supercomputers, researchers can model not just a static moment in Zeta Ophiuchi's life, but thousands of years of movement. These simulations reveal how the bow shock might have looked in the past, and how it will evolve in the future as Zeta continues to cross the galaxy. They can even show how small perturbations, such as a clump of gas or a magnetic fluctuation, might trigger changes in the shock that ripple outward like echoes in a pond. The ultimate goal of these 3D simulations is not just to reproduce what we see but to predict what we cannot yet observe. For instance, they may suggest areas where the bow shock should emit weak X-rays that current telescopes can't detect but future missions might. Or they may propose structural features, tails, turbulence, secondary arcs, that can only be seen under specific lighting conditions or wavelengths. These predictions act as a blueprint for future observations, guiding astronomers towards specific questions and new discoveries. In Zeta Ophiuchi's case, simulation has been essential in transforming a bright arc of infrared light into a fully dimensional portrait of motion, interaction, and structure. It bridges the gap between observation and theory, providing a rich, evolving context that deepens our understanding of how runaway stars behave, how bow shocks respond to galactic conditions, and how stars like Zeta carry the consequences of their past into the future. By recreating the cosmos in code, these simulations allow us to see what our eyes cannot, and to imagine the invisible forces shaping the most dramatic journeys in the galaxy. Zeta Ophiuchi is more than just a stellar curiosity, it is a cosmic key. In its blistering speed, shimmering bow shock, and solitary journey across the galaxy, this one star tells a story that cuts across multiple domains of astrophysics. By studying Zeta in detail, astronomers unlock clues about the fundamental processes that shape the universe, how stars are born, how they live and die, how they move through space, and how they influence their environment. It is in this synthesis of stellar death, galactic motion, and interstellar physics that Zeta Ophiuchi proves to be an invaluable laboratory, one that transcends its apparent isolation. At the heart of Zeta's significance lies the event that cast it adrift, the supernova of its binary companion. This explosion, though not directly observed, is evidenced in the star's velocity and the bow shock it drags through the cosmos. Studying this aspect of Zeta helps astrophysicists understand the aftermath of supernovae, how they disrupt binary systems, redistribute mass, and impart velocity to surviving stars. Supernovae are among the most important and energetic processes in the cosmos. They seed the universe with heavy elements, trigger star formation, and alter the dynamics of their surroundings. But the detailed mechanics of binary supernova ejections, especially how different mass ratios and orbital distances affect the velocity of the surviving star, are complex and not fully understood. Zeta Ophiuchi, by serving as a case study of this very phenomenon, helps to fill in those gaps. This is also where Zeta contributes to our understanding of runaway dynamics. Its measured speed, estimated trajectory, and presumed origin point in Upper Scorpius provide rare, precise data on how fast and how far a massive star can travel after ejection. Its velocity of about 24 km per second, though not the fastest among runaways, is highly informative because it's been tracked so accurately. That makes Zeta a gold standard for modeling how binary disruption events affect stellar populations over time. These events don't just scatter stars, they redistribute mass and energy across the galaxy, altering the morphology of stellar associations and affecting the chemical evolution of the Milky Way. Zeta's journey also tells us something profound about galactic motion and structure. As the star streaks through different regions of the Milky Way, it crosses varying gradients of density, magnetic fields, and chemical composition. Its movement is a probe, a kind of stellar test particle, that allows astronomers to map the unseen contours of our galaxy. By tracking Zeta's path and the shape and behavior of its bow shock, scientists can infer the structure of the interstellar medium it travels through. This includes measuring densities, turbulence, and magnetic field orientations that would otherwise be invisible. In this way, Zeta is like a litmus test that helps reveal the invisible conditions of space. The bow shock itself is another area where Zeta proves indispensable. Visible in infrared and modeled through hydrodynamic simulations, Zeta's bow shock is not just beautiful, it's a rich source of data on supersonic astrophysical interactions. When a stellar wind collides with interstellar gas at high velocity, it generates compression, heating, and radiation that mimic processes happening in far more extreme environments, such as the surroundings of black holes, the jets from young stars, or even the edges of galaxies. By studying Zeta's bow shock, astronomers can test and refine shock physics theories in a controlled, nearby setting. This kind of research can improve our understanding of shock propagation, instabilities, and energy dissipation, concepts that apply broadly across the universe. Zeta also contributes to our knowledge of stellar wind behavior. The massive outflow from O-type stars like Zeta carries momentum and mass into space at incredible rates. The interaction between this wind and the ISM not only shapes the bow shock but also informs scientists about the mass loss rates, temperature gradients, and radiative pressures that define massive stars. Since these stars evolve rapidly and end their lives in spectacular explosions, understanding how they lose mass over time is critical for predicting their final fates, whether as supernovae, neutron stars, or black holes. Moreover, Zeta Ophiuchi is an important case study in stellar isolation and environmental impact. Though no longer part of a cluster, its presence still affects the space around it. It compresses gas, heats dust, and may even help trigger star formation if it passes near a dense molecular cloud. In this way, Zeta is an example of stellar feedback, the process by which stars alter their surroundings on a galactic scale. Feedback is a key ingredient in the evolution of galaxies, and runaway stars are particularly interesting because they spread this feedback far from their points of origin. Zeta's movement means that its energy isn't just confined to one star-forming region, it's distributed along a path that spans hundreds or thousands of light years. On a broader scale, Zeta helps refine population models of stars in the Milky Way. Knowing how many runaway stars exist, how fast they travel, and how they interact with their environment allows astronomers to adjust their estimates of star formation efficiency, stellar life cycles, and binary evolution rates. Runaway stars are rare but not negligible. They represent a critical correction to otherwise cluster-based star distribution models. Zeta's well-documented case helps calibrate those corrections, giving researchers a more accurate picture of how the Milky Way evolves over time. From a technical standpoint, Zeta has also been a testing ground for observational techniques. Its brightness, proximity, and speed make it ideal for demonstrating methods in spectroscopy, astrometry, and infrared imaging. Observatories from Spitzer to Hubble to ground-based telescopes have all turned their instruments toward this star. Its strong emissions in ultraviolet and X-ray wavelengths also provide important opportunities to study high-energy radiation in stellar environments. These observations help astronomers develop better tools, instruments, and data analysis methods that can be applied to more distant or less accessible objects. Perhaps most compellingly, Zeta Ophiuchi offers a narrative bridge between the intimate and the immense. It connects the personal story of a single star's violent past to the galactic scale processes that define the Milky Way's evolution. It's a reminder that every point of light in the night sky carries with it a history of motion, interaction, and transformation. For Zeta, that history includes the death of a companion, the violence of ejection, the endurance of interstellar flight, and the beauty of a shock front that glows as a result. It also reminds us that space is not empty. It is a landscape with texture, shaped by wind, radiation, and matter in constant motion. Zeta reveals that the universe is not static or silent. It is dynamic, evolving, and filled with echoes of past events. Every ripple in its bow shock, every variation in its trajectory, every spectral line in its radiation is a page in a much larger story. A story about the life and death of stars, the structure of space, and the laws that govern the cosmos. Studying Zeta Ophiuchi is not about a single object. It's about using that object as a lens through which we can see the universe more clearly. It's about deciphering the traces left behind by violent events, understanding how energy and momentum are transferred across space, and connecting the fate of one star to the evolution of entire galaxies. That is why it matters, not just to astrophysicists, but to anyone who seeks to understand our place in this vast, dynamic universe. Zeta Ophiuchi is far more than a point of light streaking across the night sky. It is a stellar fugitive, a survivor, a witness to destruction, and a messenger from a cataclysmic past. It races not just with velocity, but with history encoded in every photon it emits. Though millions of years have passed since the explosion that changed its fate forever, Zeta still carries that moment forward, etched into its speed, its trajectory, and the turbulent shockwave it carves into space. In the grand narrative of the cosmos, it is one of the few stars that is both a consequence and a continuation of a dramatic celestial act. Calling Zeta Ophiuchi a star on the run isn't merely poetic, it's literally true. This is a star that was forcefully evicted from its home by the most violent event in stellar evolution, a supernova. When its binary companion detonated, the gravitational bond that once held Zeta in a mutual orbit shattered instantly. The immense loss of mass from the exploding star unbalanced the system, and Zeta was catapulted outward, like a cannonball fired across the galaxy. Its current speed of around 24 kilometers per second might not sound tremendous by Earth standards, but in cosmic terms, it's a breakneck pace, fast enough to outrun entire star clusters and carve a solitary path through the galaxy for millions of years. And yet, despite being hurled from its home, Zeta Ophiuchi didn't die. On the contrary, it shines brighter than most. As an O-type star, it's among the most luminous and massive in the galaxy. Its fierce light radiates across the electromagnetic spectrum, visible, ultraviolet, and even X-rays, making it a stellar lighthouse in the darkness. In that sense, it is not only a runaway but a beacon, visible proof that stars can be transformed, not extinguished, by cosmic violence. It may have lost its companion, but it has gained a kind of singular legacy, a chance to be studied, admired, and remembered long after the explosion that set it loose. What makes Zeta even more fascinating is that it is, in every moment, interacting with the galaxy around it. Its movement is not a simple arc through empty space, it is an active disruption. The stellar wind it emits, millions of particles flowing outward every second, crashes into the interstellar medium, creating shockwaves and heating the gas to glowing temperatures. Its bow shock is like a permanent flare, a visible mark of its flight through space. As it continues its journey, it leaves behind a faint trail, awake in the galactic sea, just as a ship leaves ripples in the water long after it has passed. This visible wake, this interaction with dust and gas, adds another layer to its story. Zeta Ophiuchi, in its loneliness, is still altering the environment it passes through. It sculpts space as it moves, heating the dust, ionizing gas, and potentially even compressing materials enough to ignite new generations of stars. In this way, its journey is not just one of survival but of influence. It is not merely a witness to past destruction, it is a catalyst for future creation. Even more compelling is the fact that Zeta's running is not aimless. Its path can be traced back to the Upper Scorpius-Ob association, where it likely formed. That link to its origin makes Zeta one of the rare stars for which we can construct an almost complete timeline, from birth to ejection to current motion. This continuity transforms Zeta from a simple object of study into a narrative entity, one that allows scientists to explore long-term stellar evolution, the effects of binary interaction, and the feedback loop between stars and their environments. And this journey is far from over. Zeta is still burning hot and bright, fusing hydrogen in its core, though at a furious pace. Like all massive stars, its life will be short by cosmic standards, just a few million more years before it, too, reaches the end of its road. But that end will not be quiet. Zeta Ophiuchi is destined to become a supernova itself, continuing the cycle that began with the death of its partner. Its final explosion will once again reshape its corner of the galaxy, possibly giving birth to new stars, blowing apart clouds of gas, or enriching the interstellar medium with heavy elements forged in its core. In that moment, Zeta will no longer be a star on the run. It will be a star transformed, completing a journey that began in companionship, turned to solitude, and ends in brilliance. Until then, it continues to teach us. Every time we observe its bow shock, its spectral lines, its motion through the galaxy, we are learning, not just about Zeta, but about all stars that have suffered a similar fate. Each runaway star, like Zeta, is a puzzle piece in the larger picture of how stars form, live, interact, and die. But few are as vivid or as informative as Zeta Ophiuchi. Its brightness, its motion, its history, all conspire to make it one of the most instructive and awe-inspiring runaways known. It reminds us that violence and beauty are often intertwined in space. That a star can be both a victim of tragedy and a symbol of endurance. That motion itself can be a legacy, written not in words but in starlight and shockwaves. So when we gaze up at the constellation Ophiuchus and glimpse the distant gleam of Zeta Ophiuchi, we are not just looking at a star. We are looking at momentum given form, and memory made luminous. We are witnessing a story still in motion, one forged in fire, hurled through silence, and destined to end in light. In the vast theater of the cosmos, every star has a role. Some burn quietly, some dance in binary waltzes, and others explode in spectacular finales. But Zeta Ophiuchi's story is different. It is not defined solely by its birth or its future death, but by what it survived, and what it fled. Like a fugitive fleeing the blast of a cosmic crime, it carries with it the momentum of a loss so violent, so final, that even time cannot erase its consequences. Zeta Ophiuchi is a living echo of an explosion, a remnant of destruction, and a testament to the raw, unrelenting power that shapes our universe. That explosion, the supernova of its massive binary companion, was not just an event, it was a punctuation mark in the life of a star. The sudden collapse and detonation ripped apart the gravitational bond between two massive stellar bodies, and with it, tore open a pathway that would cast Zeta into galactic exile. This exile wasn't a passive drift, it was a launch. A recoil. A blast wave journey initiated by death itself. And from that moment forward, Zeta Ophiuchi has traveled alone, a star forever bearing the signature of its origin story, velocity born of catastrophe. But this fugitive has not run silently. It leaves behind a trail, a glowing bow shock in the fabric of space, a compressed wave of light and gas that broadcasts its movement to all who can observe. Every arc of glowing dust, every ripple of compressed hydrogen, every shimmer in the infrared is a whisper of the explosion that hurled it forward. And though the supernova that launched Zeta is long gone, its effects ripple forward in time, preserved in the trajectory, the bow shock, and the spectral identity of the star that survived. There is a certain irony in the fate of Zeta Ophiuchi. The companion that exploded, the star that died, is now silent, possibly a neutron star, maybe a black hole, or even scattered dust. And yet, it is Zeta that remains visible. It is Zeta that shines. It is Zeta that carries the story. The death of its partner may have been the most dramatic moment, but Zeta's continued life is what gives that moment context. Without Zeta, the supernova would be lost to history. With it, the story remains alive, unfolding in real time as the star slices through space. This idea, that an event so sudden and violent can have effects so prolonged and beautiful, is one of the most profound lessons of Zeta's existence. It is a reminder that the universe does not forget. That energy must go somewhere. That loss can translate into motion, into light, into new beginnings in unexpected places. Even the violence of a stellar death becomes the engine for a new chapter. And what a chapter Zeta is writing. In its short lifetime, itself only a fleeting blink on cosmic scales, it has traveled vast distances, passed through interstellar landscapes, influenced the environments it touched, and become a guidepost for astronomers seeking to understand the deeper laws of the universe. It has shown us how stars escape their homes, how wind shapes shocks, how movement leaves traces, and how the legacy of a supernova can endure not just in radiation or debris, but in the continued life of what was left behind. Zeta Ophiuchi's journey also gives us a rare look into the cycles of stellar evolution. Born from a cloud of gas, entangled in a binary relationship, ejected by a supernova, and now fated to explode itself, it illustrates the closed-loop nature of astrophysics. One death leads to another birth. One explosion leads to another shockwave. The energy of stars is never wasted. It is transformed, transmitted, and sometimes carried across hundreds of light years in the momentum of a single, fleeing survivor. And that survivor is not forgotten. Zeta Ophiuchi stands today not just as a point of study but as a symbol. A symbol of how stars interact, how systems can shatter, and how even in the aftermath of destruction, there is continuity. There is trajectory. There is meaning. The death of Zeta's companion might have seemed like an end, but in reality, it was a beginning of a journey that we, from our vantage point on Earth, are privileged to witness. As we look toward the sky, toward the serpent-bearer constellation Ophiuchus, and seek out that piercing blue point of light that is Zeta Ophiuchi, we are not just looking at a star. We are peering into a story that began millions of years ago with fire and force, and one that continues even now. Every photon it emits is a message sent across the ages. A testament not just to its own endurance, but to the transformational power of the universe. And perhaps, in its final act, Zeta will complete the circle. One day, when its fuel is gone and its core can no longer resist gravity, it too will explode. It too will leave behind remnants, a shockwave, and maybe even a new generation of stars. And perhaps, just like its companion before it, its final breath will send yet another star, yet another fugitive, on its own journey through the galaxy. In that way, Zeta Ophiuchi is more than a survivor of stellar death. It is a link in an endless chain, a chapter in a story that stretches across the stars. It is the echo of an explosion, one that still resonates today, not as a fading memory, but as a vibrant presence streaking through the galaxy, alive with motion, light, and meaning. And as long as we keep watching the skies, we will hear that echo. Still moving. Still burning. Still telling the tale. This video is for educational or entertainment purposes only, and information provided in the video may be incorrect. Like the video and subscribe to the channel for more such amazing videos.